What if the world was known once, completely, precisely, long before history learned to speak? What if maps existed, drawn with impossible accuracy? Before the age of satellites, before compasses split the cardinal points, before any nation claimed dominion over uncharted waters? What if those maps showed coastlines buried now beneath miles of ice, rivers that vanished 12,000 years ago, mountains drowned under glacial silence? What if someone mapped the Earth when the Earth looked different? Not a question of technology, a question of memory, of something the ice swallowed whole and never gave back. Something that sleeps in the white quiet of Antarctica, pressed flat beneath the weight of forgetting. Tonight, we follow that whisper, not as historians chasing conquest, not as explorers planting flags, but as listeners, patient, still, waiting for the planet to speak in its own time, in its own buried language. Because some knowledge doesn't fade, it freezes, and when the world thaws, even slightly, it begins to bleed back through. Let the night settle around you. Let your breath slow to the rhythm of glaciers. This is not a story of answers. This is a story of ice. And what lies beneath it? Of maps drawn in an age we were never supposed to remember. Close your eyes if you need to. The story will still be here. It always has been. There are objects in the world that do not belong to their time. Not in the way of prophecy or magic, in the way of precision, of knowledge arrived too early, drawn too clearly, positioned with an accuracy that should not yet exist. A map, for instance. Ink on gazelle skin. Lines tracing coastlines no explorer of that century had ever seen. Mountains placed where mountains stood, though no ship had yet sailed close enough to chart them. In 1513, a Turkish admiral named Piri Reis compiled a map of the known world. He worked in Constantinople, in the shadow of empire, copying from older sources, charts and fragments gathered from sailors, from libraries, from the plundered archives of conquered lands. His map showed the Atlantic. It showed the coasts of Africa, of South America, of islands scattered like breadcrumbs across an uncharted sea. But it also showed something else. It showed a coastline, one that matched, with startling accuracy, the northern edge of Antarctica, not as it appears today, locked beneath miles of ice, but as it would have looked thousands of years ago. But the land was free and the rivers ran warm into an open sea. Piri Reis did not discover this coastline. He copied it from sources, he said, that were ancient even in his time, from maps drawn long before the age of exploration, long before the compass guided ships across unknown waters. He did not understand what he was copying. He only knew the lines were there, precise and undeniable, traced from something far older than his century could explain. The map should not exist, but it does, and it is not alone. In 1531, a French cartographer named Orontius Phineas created another map. This one showed the entire continent of Antarctica, its rivers, its mountains, its inland seas, depicted with such detail that modern researchers, using ground-penetrating radar and seismic imaging, have confirmed the accuracy of features buried now beneath 2 miles of ice. Features no human should have been able to see, let alone map, in the 16th century. Phineas, like Piri Reis, did not sail to Antarctica. He did not discover it. He copied his map from older sources, sources now lost, sources that somehow preserve the memory of a continent as it existed long before the ice claimed it. These maps are not myths. They are objects. Ink on parchment, lines drawn with intention, with measurement, with a knowledge that defies the official narrative of human exploration. And so the question forms, quiet and persistent, like water seeping through stone. Who mapped the world before the ice came? Not gods, not visitors from distant stars. People, navigators who understood the stars, the tides, the way currents pull ships toward unseen shores. Cartographers who traveled coastlines now drowned, who climbed mountains now submerged, who recorded the world as it was, not as we imagine it, not as history teaches it, but as it actually looked in an age we were never supposed to remember. The ice came slowly at first, then all at once. 12,000 years ago, the Pleistocene glaciers began their final retreat, melting in surges that flooded coastlines, drowned valleys, erased entire landscapes beneath rising seas. The world was redrawn, and with it, the memory of what had stood before. But maps are stubborn things. They survive in ways cities do not. They are copied, recopied, passed from hand to hand, from empire to empire, carried forward through centuries by sailors who do not always understand what they hold. A map does not need to be believed. It only needs to be preserved. And so the knowledge survived. Fragmentary, distorted, passed through the hands of Phoenician traders, Arab scholars, Byzantine librarians, Ottoman admirals. Each generation copying the lines, tracing the coasts, preserving something they could not fully comprehend. The maps themselves became ghosts, echoes of a world no longer visible, copied forward into an age that could no longer verify their accuracy, because the geography they depicted had vanished beneath ice and ocean. But the lines remained, precise, undeniable, waiting. The Piri Reis map was rediscovered in 1929, tucked away in the archives of the Topkapi Palace in Istanbul. For years, it was studied as a historical curiosity, a beautiful artifact of Renaissance cartography. But in the 1960s, a U.S. Air Force officer and cartographer named Charles Hapgood examined it more closely. He compared the coastlines on the map to modern seismic surveys of Antarctica. He measured the latitudes, the river placements, the mountain ranges, and he found that they matched. Not approximately, not symbolically. They matched with a precision that suggested the original source maps, whatever Piri Reis had been copying from, were created using spherical trigonometry, an advanced mathematical technique not commonly used in Europe until the 18th century. The map did not guess at Antarctica's shape. It knew it. Hapgood proposed a theory, not a comfortable one. He suggested that the source maps might have originated from a lost maritime civilization, one that existed during a warmer climatic period, one that sailed and charted the world before the ice locked the poles in place. He did not name this civilization. He did not claim to know who they were or where they came from. He only pointed to the maps and said, "Someone made these. Someone who knew the earth as we do not." The academic world did not embrace the theory. It was too far outside the boundaries of accepted history, too threatening to the carefully constructed timeline of human civilization. And so it was filed away, footnoted, left to gather dust in the same archives that had once hidden the maps themselves. But the maps did not disappear. They continued to exist, silent and patient, holding their impossible knowledge like seeds waiting for the right season to bloom. There is a moment in the examination of any impossible object when belief stops mattering, when the question is no longer can this be real, but simply what does this mean? The Piri Reis map exists. The Orontius Phineas chart exists. They are not paintings, not myths, not dreams transcribed onto parchment by mystics in candlelit rooms. They are cartographic documents, signed and dated, preserved in archives, studied by scholars, measured against satellite data and seismic surveys. And the measurements align. Not perfectly. Nothing that survives across centuries remains perfect, but enough. Enough to disturb the comfortable narrative of exploration, the timeline that places Antarctica's discovery in the 19th century, its true shape revealed only in the 20th. Because the maps show Antarctica as it was not when they were drawn, but as it existed thousands of years before, when the coastline was free. But rivers carved through valleys now buried under glacial silence. But the land itself was something other than the frozen void we know today. In 1949, a Swedish-British Antarctic expedition conducted seismic profiling across Queen Maud Land, measuring the topography hidden beneath the ice. The data revealed coastlines, mountain ranges, river valleys, all invisible to the naked eye, all locked beneath a mile of frozen water. When researchers later compared these seismic profiles to the southern coastline depicted on the Piri Reis map, they found what one U.S. cartographic evaluation described as remarkable agreement. The geographical detail matched the subglacial landscape with a precision that suggested the original source maps. Whatever Piri Reis had copied in 1513 were drawn when that coastline was still visible, still accessible, still known. The ice cap in that region is now about a mile thick. It has been thick for at least 15 million years, though the exact timing of Antarctica's full glaciation remains a subject of quiet debate among paleoclimatologists. But the maps do not care about debates. They simply exist, holding their lines, their latitudes, their impossible knowledge like a breath held too long underwater. Orontius Phineas, working in 1531, produced a map that showed the entire Antarctic continent in startling detail. Not as a vague blob at the edge of the known world, but as a landmass with rivers, with interior features, with a shape that modern radar imaging has since confirmed lies hidden beneath the ice. He did not sail there. He did not discover it. He copied it from older sources, sources that have since vanished, dissolved into the same historical fog that swallowed the civilizations who first charted those coasts. The maps are ghosts, echoes of something that should not exist, but does. And they whisper a single, unsettling question. Who was here before us? Not all mysteries demand solving. Some are meant to be held, like stones smoothed by water, turning them over and over in the mind until the edges soften and the question itself becomes a kind of answer. The maps suggest a maritime culture. Not a single empire, not a centralized state with monuments and written histories, but something more dispersed. Networks of sailors who understood the stars, who read the pull of currents, who navigated by the rhythms of wind and tide. They would have lived during a warmer climatic period, possibly during the Holocene optimum or even earlier, when the poles were not yet locked in their current frozen permanence. They would have sailed coastlines that are now drowned, charted islands that are now submerged, built ports on shores that the rising seas claimed long before writing began its careful accounting of human achievement. Their cities, if they had cities, are gone, dissolved into silt, crushed beneath tectonic drift, swallowed by the ocean's patient hunger. But their maps survived. Because maps are portable. Maps are copied. Maps move through time in ways architecture cannot, in ways monuments cannot. A stone temple crumbles. A map is traced onto new parchment and carries forward, generation after generation, copied by hands that do not understand what they preserve, but preserve it nonetheless. Piri Reis himself noted this. In the margins of his map, he wrote that he had compiled it from 20 different source charts, some Portuguese, some Arab, some Greek, some of unknown origin. He mentioned a map used by Christopher Columbus, one that Columbus himself claimed came from the Library of Alexandria, the great archive destroyed in antiquity, its contents scattered across the known world. Whether that claim is true does not matter. What matters is the pattern, knowledge moving through channels we no longer have access to, preserved in fragments, in copies of copies, in charts redrawn by cultures who could no longer verify their accuracy because the world they depicted had already changed beyond recognition. The ice came, the seas rose, the coastlines shifted, and the knowledge became orphaned, accurate, precise, but belonging to no living memory, no verifiable voyage, no expedition that history could name. And so the maps became mysteries, objects out of time, not because they were created by magic, but because the world they recorded no longer exists. There is a concept in geology called unconformity. It describes a gap in the rock record, a missing chapter where erosion or non-deposition has erased millions of years of history. The layers above and below remain. But the middle is gone, but geologists must infer what happened during that absent time by studying what came before and what came after. Human history has unconformities too, gaps where the record goes silent, periods where we know something must have happened because the evidence appears later, fully formed, but the intervening steps are lost. Writing, for instance, appears suddenly in Sumer, in Egypt, in the Indus Valley, as if it had always existed. Agriculture blooms almost simultaneously across disparate continents. Astronomical knowledge, sophisticated and precise, shows up in cultures separated by oceans and millennia, with no clear line of transmission. The maps are another unconformity, a gap where knowledge exists without a visible source, where precision appears without the expected centuries of trial and error. They suggest something that history has not preserved, a culture or cultures who sailed and mapped the world during a climatic window we barely understand, whose legacy survived only in fragments, copied forward into an age that no longer remembered where the knowledge came from. The academic response has been, largely, to dismiss the maps as misinterpretations, to argue that what appears to be Antarctica is actually an extension of South America, distorted by the limits of 16th century cartography, to suggest that the ancient coastlines are simply artistic flourishes, inventions meant to fill empty space on the parchment. And perhaps that is true. Perhaps the resemblance is coincidence, the alignment a trick of projection and scale. But the maps do not argue. They do not defend themselves. They simply sit in their archives, silent and patient, waiting for anyone willing to look closely enough to see what they hold. And what they hold is this: the world as it was, as the ice. There is another way to understand the maps, not through cartography or mathematics, but through time itself, through the slow, patient unfolding of climate and ice, the way the planet breathes across millennia, expanding and contracting, freezing and melting, rewriting its own surface in cycles so vast that human memory cannot hold them whole. 12,000 years ago, the Earth was finishing a conversation with ice. The Pleistocene glaciers had held the northern hemisphere in their grip for 90,000 years, locking water into vast continental sheets that stretched from the Arctic to the edges of what would become New York, London, Berlin. Sea levels sat lower. Some estimates placed them 400 feet below present levels, and coastlines extended far beyond where they rest today. Land bridges connected continents. Islands that are now scattered across empty ocean were once mountains in continuous landscapes. The world was larger then. Or perhaps it only felt larger, because so much of it has since been drowned. The ice began to retreat around 19,000 years ago, melting in surges and pauses, releasing water back into the oceans in pulses that geologists now call meltwater events. The first major pulse, Meltwater Pulse 1A, occurred around 14,600 years ago and raised global sea levels by perhaps 50 to 80 feet in the span of just a few centuries. Coastlines that had been stable for thousands of years suddenly vanished. River deltas shifted inland. Ports became bays. Cities, if there were cities, drowned. Then came the Younger Dryas, a sudden, brutal return to cold that lasted from roughly 12,900 to 11,700 years ago. The warming paused. The ice sheet stabilized. Sea level rise slowed to a crawl, perhaps only 4 to 8 millimeters per year, a pace gentle enough that coastal communities might have adapted, might have built again along shores they thought were safe. But the pause was temporary, a held breath before the final exhale. When the Younger Dryas ended, the ice melted faster than it ever had before. Another pulse, Meltwater Pulse 1b, flooded the world between 11,500 and 11,000 years ago, raising sea levels by at least 20 feet, possibly as much as 90, depending on which ice sheets contributed and how fast they collapsed. The exact numbers remain debated, contested by geologists who study sediment cores and coral terraces, who measure isotopes in ancient ice and calculate the mass balance of glaciers that no longer exist. But the direction is not debated. The seas rose fast, and they took with them any civilization unlucky enough to have been living along the coasts during that narrow, catastrophic window. If someone had mapped the world before that flood, if they had sailed and charted and recorded coastlines during the warmer period that preceded the Younger Dryas, or during the cold pause itself, their maps would show a world that no longer exists. They would show Antarctica with rivers, because the ice had not yet fully locked the continent. They would show coastlines hundreds of miles seaward of where they sit today. They would show islands and harbors and river mouths that are now submerged beneath 300 feet of water, invisible, drowned, forgotten. And if those maps were copied forward, passed from culture to culture, redrawn by scribes who no longer understood what they depicted, preserved not because they were believed, but simply because they existed, then they would eventually land in the hands of a Turkish admiral in 1513. Or a French cartographer in 1531, who would trace the lines without comprehension, without context, without any way to verify the impossible accuracy of what they were copying. The maps would become artifacts out of time, precise echoes of a world erased by water. The Holocene climatic optimum arrived a few thousand years after the floods. Between roughly 9,000 and 5,000 years ago, global temperatures peaked higher than they are today, perhaps 2 to 4 degrees Celsius warmer in the northern hemisphere, depending on the region. Glaciers retreated further. The ice caps shrank. Antarctica's edges may have been exposed, at least partially, at least along certain coasts where the warming was strong enough to melt the thinner ice. This was the warmest period of the current interglacial. The climate that birthed agriculture, that allowed the first cities to rise in Mesopotamia and the Nile Valley, that gave humanity the stability it needed to stop wandering and start building. It was also the climate during which any surviving maritime cultures, those who had lived through the floods, who had preserved their knowledge through oral tradition or copied maps or some other means we no longer understand, would have had access to coastlines and sea routes we cannot access today. They could have sailed to Antarctica, not to the interior, not to the deep frozen plateau, but to the coasts, to the valleys where rivers flowed during summer thaws, to the harbors where ice retreated enough to allow landing. They could have mapped it, not perfectly, not completely, but enough. Enough to record the shape of the land, the placement of mountains, the flow of water through subglacial valleys that are now invisible beneath miles of ice. And then the climate cooled again. Slowly, over millennia, temperatures dropped back toward the levels we know today. The ice expanded. The coastlines disappeared. And whatever knowledge had been gathered during that narrow warm window became obsolete, geographically accurate, but no longer verifiable, because the world it described was gone. The maps orphaned themselves. They became relics of a climate that no longer existed, preserved by cultures who could not understand their significance because the reference points, the actual coastlines, the actual rivers, the actual mountains, were buried under ice or drowned beneath risen seas. And so the maps waited, silent, patient, holding their impossible knowledge like seeds in frozen ground, waiting for a future warm enough to recognize what they were. Navigation before satellites, before compasses, before instruments that could measure longitude with mechanical precision, was an art of intimacy with the sky. Sailors read the stars the way others read books, not casually, but with the kind of attention that keeps you alive. They knew which constellations rose in which seasons, which stars sat fixed near the poles, which moved across the horizon in predictable arcs. They measured the height of the North Star with simple tools: a camal, a wooden plate held at arm's length, a string tied to mark the angle between star and horizon. From that single measurement, latitude could be determined. Not perfectly, but close enough. The Phoenicians sailed this way 4,000 years ago, crossing the Mediterranean in the dark, guided by Polaris and the movement of constellations, by the depth of water measured with weighted lines, by the flight patterns of seabirds returning to unseen coasts. They did not have charts in the way we understand them, but they had knowledge, oral, encoded, passed from navigator to navigator in the form of sailing directions, star paths, seasonal wind patterns. Knowledge that lived in memory, in practice, in the bodies of those who spent their lives reading the language of ocean and sky. The ancient Greeks followed. They developed the Antikythera mechanism, a bronze device of gears and wheels that tracked the movements of celestial bodies, that predicted eclipses and planetary positions, essentially the world's first analog computer, used possibly for navigation in the 3rd or 2nd century BC. They understood spherical geometry, the way lines curve across the surface of a globe, the mathematics required to translate observations of stars into positions on a map. And then came the Islamic Golden Age. Between the 8th and 13th centuries, scholars in Baghdad, Cairo, Moraga, and other centers of learning refined the mathematics of navigation into something approaching modern precision. They developed spherical trigonometry, the branch of mathematics that allows accurate mapping on a curved surface that translates three-dimensional observations into two-dimensional charts. Nasir al-Din al-Tusi, working in the Moraga Observatory in the 13th century, compiled astronomical tables and geographical coordinates for 256 cities stretching from Cordoba to Peking. His work became the foundation for later European cartography, copied and translated and absorbed into the map-making traditions that would eventually produce the charts used by Columbus, by Magellan, by Piri Reis. This was not primitive guesswork. This was science, rigorous, mathematical, tested across thousands of miles of ocean. And it worked. Ships crossed seas they had never seen before and found the islands they were searching for. Coastlines were charted with increasing accuracy. The world began to take shape on parchment, its proportions and distances measured not by myth, but by observation. But the knowledge did not begin in the 13th century. It was refined then, codified, written down in forms that survived. The sailing itself, the practice of crossing oceans, of navigating by stars, of mapping coastlines, was far older. How much older? No one can say with certainty, because the oldest maps, the oldest sailing directions, the oldest records of who went where and when, those were lost. Many of them burned at Alexandria. The Library of Alexandria was not simply a building. It was an archive, a museum, a research institution, a repository for the collected knowledge of the ancient world. Founded in the 3rd century BC by Ptolemy I, It grew to hold an estimated 500,000 documents, scrolls from Assyria, Greece, Persia, Egypt, India, lands whose names have since been forgotten. Scholars lived there full-time, translating, copying, studying texts that spanned centuries of accumulated wisdom. If there were ancient maps, charts compiled by Phoenician sailors, by Egyptian expeditions down the African coast, by explorers whose voyages were never recorded in surviving histories, they would have been kept there. In 48 BC, during the civil war between Julius Caesar and Ptolemy XIII, fire consumed part of the library. How much was lost in that blaze remains unknown. Some ancient sources claim the entire collection burned. Others suggest only a portion was destroyed, and that the library continued to function for centuries afterward, gradually declining through neglect and political upheaval until it finally disappeared sometime in the late Roman period. The exact details do not matter. What matters is this: the single greatest archive of ancient knowledge was destroyed, and with it, any chance of verifying the origins of the maps that survived in copied form centuries later. Piri Reis himself noted that one of his source maps came from the time of Alexander the Great, possibly from the Library of Alexandria. Whether that claim is accurate is impossible to confirm. The original is gone. Only the copies remain, traced and retraced through Byzantine scholars, Arab navigators, Renaissance cartographers, each generation preserving lines they could no longer verify, because the world those lines depicted had changed beyond recognition. The maps became orphans, accurate, precise, but belonging to no verified voyage, no documented expedition, no history that the official record was willing to accept. And so they sat in archives, filed away as curiosities, as beautiful anomalies, as objects that suggested something impossible, that someone, long before the age we call the age of exploration, had already explored. A ship is a statement of intent, not just to cross water, but to return, to carry cargo, knowledge, people across distances that cannot be walked. The ancient world understood this. They built vessels not from guesswork, but from generations of accumulated wisdom. Each plank shaped by the memory of storms survived, each joint reinforced by the lesson of hulls that split and sank. The Phoenicians, working from the coastal cities of Tyre, Sidon, and Byblos between 1550 and 300 BCE, became the maritime spine of the ancient Mediterranean. Their ships were not primitive rafts. They were engineered craft, built using shell-first construction, where the outer hull was assembled first, each plank edge joined to the next with mortise and tenon joints locked together, creating a structure strong enough to withstand open ocean swells. The frames came later, fitted inside to reinforce what had already been made watertight. It was labor-intensive. It required skilled woodworkers who understood how timber swells in water, how grain direction affects strength, how to seal seams with pitch and resin to keep the sea outside where it belongs. These ships crossed vast distances. The Phoenicians sailed not just the Mediterranean, but ventured beyond the Pillars of Hercules, the Strait of Gibraltar, into the Atlantic, reaching the British Isles to trade for tin and copper, pushing down the African coast, establishing colonies as far west as Carthage and Cadiz. They did this without compasses, without GPS, without any of the instruments we consider essential. They navigated by stars, by the color of water, by the flight patterns of seabirds returning to land. They understood currents, wind patterns, seasonal shifts. They knew which routes to take in summer, which to avoid in winter, where fresh water could be found on distant islands. This was not exploration in the modern sense, the planting of flags, the claiming of territory. This was trade. The movement of goods, cedar timber, Tyrian purple dye, glassware, pottery, metals, across networks that linked Egypt with Greece, North Africa with Spain, the Levant with Britain. And trade requires return voyages. It requires maps, or at least mental maps, sailing directions passed from captain to captain, knowledge encoded in oral tradition and later written down, copied, preserved because it had economic value. Or it kept ships from being lost. Or it allowed empires to grow wealthy on the flow of goods from one end of the known world to the other. The Minoans, working from Crete 1,000 years earlier, built ships with slender hulls and rectangular sails, vessels designed for speed and maneuverability, capable of long ocean voyages. Their frescoes, preserved in volcanic ash at Akrotiri, show fleets of ships, dolphins leaping beside hulls, a maritime culture so sophisticated it dominated Aegean trade for centuries. When their civilization collapsed, possibly due to the eruption of Thera around 1600 BCE, their shipbuilding knowledge did not vanish. It passed to the Greeks, to the Phoenicians, to the cultures that followed, each adding refinements, each learning from the failures and successes of those who came before. By the time of the Romans, ships were being built using frame-first construction, the method that dominates modern shipbuilding, where the internal skeleton is erected first and the planking added afterward, allowing for larger, stronger vessels capable of carrying immense cargoes across open ocean. But the older methods, the shell-first technique, the mortise and tenon joints, continued in use for smaller craft, for vessels operating in coastal waters, for ships built by cultures that had not yet adopted Roman engineering. The point is this: by the time the maps appeared in the hands of Piri Reis and Orontius Phineas, humanity had been building ocean-going vessels for at least 4,000 years. Possibly longer. The technology existed. The navigational knowledge existed. The mathematics for spherical trigonometry existed, at least in the Islamic Golden Age. And possibly earlier in forms that did not survive. What was missing was not capability. What was missing was motive. Why would anyone sail to Antarctica before it was discovered in the 19th century? But the question assumes Antarctica has always been frozen. And that assumption, as the maps quietly suggest, may be wrong. There is another piece to this puzzle, one that academic consensus has largely dismissed, but that refuses to completely fade from consideration: the possibility of transoceanic contact before Columbus, before the Vikings, before any voyage that history officially records. The Norse reached Newfoundland around 1000 CE. This is not debated. Lance aux Meadows is physical proof, a settlement with Norse artifacts, with structures built in the Scandinavian style, 500 years before Columbus crossed the Atlantic. But there are other suggestions, less certain, more controversial. Genetic studies published between 2004 and recent years have found traces of Polynesian DNA in indigenous populations along the coast of South America, with contact estimated around 1200 CE. The admixture is small but distinct, suggesting a single contact event, perhaps a single voyage, a Polynesian vessel blown off course or deliberately exploring, making landfall, interacting with coastal peoples, and leaving behind a genetic signature that persisted through centuries. If Polynesians could cross the Pacific in outrigger canoes, and they did, settling islands thousands of miles from any continental shore, then what else was possible? What other cultures, in other climatic periods, might have sailed routes we no longer consider feasible because the world has changed, because coastlines have shifted, because the climate that allowed those voyages no longer exists? The academic response is caution, skepticism, a refusal to accept extraordinary claims without extraordinary evidence. And that is reasonable. Most claims of pre-Columbian contact are speculative, based on ambiguous artifacts, on cultural similarities that could be coincidence, on stories passed through so many retellings that their original form is unrecoverable. But the maps are not stories. They are objects, and they suggest, with their impossible accuracy, that someone, some culture, some network of navigators, sailed and charted coastlines that should not have been accessible, that recorded features now hidden beneath ice, that preserved their knowledge through channels we can no longer fully trace. The maps do not prove a lost civilization. They do not prove anything, except that cartographic knowledge existed that predates the official timeline of exploration. Knowledge precise enough to match modern seismic surveys, detailed enough to show rivers and mountains now buried under glaciers, old enough to have been copied and recopied through centuries until the source was forgotten and only the lines remained. And those lines, silent and patient, still wait in their archives, holding a question the world has not yet decided how to answer. The earth has drowned entire epics, not in metaphor, not in myth, in water, cold, patient, rising at rates that human memory could track, could measure, could watch as it swallowed the places where generations had lived. Sea levels that sat 400 feet lower than they rest today. Coastlines that stretched miles beyond present shores. River valleys that carried fresh water into seas that no longer exist in the same shape, the same depth, the same relationship to land. 12,000 years ago, the world was finishing a long conversation with ice. The Pleistocene glaciers, walls of frozen water 2 miles thick, stretching from the Arctic to what would become New York, Chicago, London, had held the northern hemisphere in a cold grip for 90,000 years. Then they began to melt, slowly at first, then faster, then in pulses so sudden that coastlines vanished within lifetimes, that river deltas shifted inland by miles, that entire landscapes were redrawn as if the planet had decided to start over. Anyone living along those coasts would have noticed, not in a single day, not in a single storm, but across years, across generations. The beach where their grandparents fished would be underwater. The harbor where ships once moored would sit beneath fathoms of risen sea. The trade routes that connected coastal settlements would be severed, drowned, erased from geography as thoroughly as if they had never existed. And with them, the memory. Because when the land disappears, so does the evidence. The ports become shipwrecks. The streets become sediment. The temples become reef. And the people who lived there, if they survived, moved inland, carried forward what they could, and left behind everything too heavy to carry, including the history of the world as it had been before the water came. This is not speculation. This is geology. This is archaeology conducted underwater, in the cold darkness where cities still stand, drowned but not destroyed, waiting in suspension for the technology to finally reach them. Around 14,600 years ago, the first major pulse of meltwater, what geologists call Meltwater Pulse 1A, released enough water to raise global sea levels by 50 to 80 feet in the span of a few centuries. For context, that is roughly the height of a 5-story building. Imagine the ocean rising that much in the lifetime of a single settlement, perhaps 3 or 4 generations. Fast enough that the elders would remember when the shore was farther out. Fast enough that children would ask why the old harbor is now underwater. Fast enough to force migration, abandonment, the rewriting of entire cultures around a geography that would not stop changing. Then came the Younger Dryas, a sudden return to cold that lasted from approximately 12,900 to 11,700 years ago. The warming stopped. The glaciers stabilized. Sea level rise slowed to a crawl, perhaps only 4 to 8 millimeters per year, a pace gentle enough that coastal communities might have rebuilt, might have thought the worst was over, might have established new settlements along shores they believed were safe. Some researchers have proposed that the Younger Dryas was triggered by a cosmic impact, a fragmented comet or meteor exploding in the atmosphere over North America, triggering wildfires, disrupting climate systems, causing a near-glacial rebound that lasted more than 1,000 years. The hypothesis remains controversial, widely debated, with evidence including elevated platinum levels, microspherules, melt glass, and shock-fractured quartz found at sites across North America and Europe dated to approximately 12,900 years ago. Critics point to inconsistencies, to the lack of a definitive impact crater, to the difficulty in replicating some of the reported findings. The debate continues, unresolved, a question mark hanging over one of the most abrupt climate shifts in recent geological history. But the cause does not change the effect. For over 1,000 years, the world stayed cold. The ice held. The seas paused. And anyone living along the coast had a window, a narrow, temporary window, to adapt, to build, to believe the rising water had finally stopped. It had not. When the Younger Dryas ended around 11,700 years ago, the ice began to melt again. Faster this time. Another pulse, Meltwater Pulse 1b, flooded the world between 11,500 and 11,000 years ago, raising sea levels by at least 20 feet, possibly as much as 90, depending on which ice sheets contributed and how quickly they collapsed. Entire coastlines disappeared. Islands became seamounts. Land bridges that had connected continents for thousands of years, Beringia, Doggerland, Sundaland, were severed, submerged, turned into shallow seas that slowly deepened as the water continued to rise. The Mediterranean rose 4 to 7 millimeters per year during the Neolithic period, a rate that translated to roughly 12 to 21 centimeters in a human lifetime, up to 70 centimeters in a century. That may not sound catastrophic, but it was relentless. Year after year, decade after decade, the water advanced. Storms that once broke harmlessly on distant beaches now reached the village. High tides that once stayed below the settlement now flooded streets. Freshwater wells became brackish. Fields turned to marsh. And eventually, the choice became clear: build defenses or leave. At Tel Rise, on the Carmel coast of what is now Israel, Neolithic villagers chose to fight. Around 7,000 years ago, they constructed a seawall, over 100 meters long, built from boulders sourced from riverbeds 1 to 2 kilometers away, each stone carried and placed with the singular purpose of holding back the sea. It was the oldest known coastal defense system ever discovered. Not a symbolic gesture. An engineered structure designed to protect homes, fields, lives from the advancing water. It did not work. The sea continued to rise. The storms continued to worsen. And eventually, the village was abandoned, its streets and homes submerged, its seawall still standing underwater like a monument to a battle that could not be won. The site was rediscovered in the 1960s, but it was not until 2012. But natural processes exposed previously hidden areas that archaeologists recognized the seawall for what it was: evidence that humanity's struggle against rising oceans stretches back thousands of years. But that the outcome, but as now, was often the same: abandonment, migration, the loss of place, of home, of the land that held the memory of ancestors, now drowned beneath water that does not remember and does not mourn. There was a land between Britain and Europe, not a narrow strip, not a seasonal crossing, a country, flat, marshy, crossed by rivers, rich in game, home to tens of thousands of people who lived there for 6,000 years without knowing the sea would one day claim it all. Doggerland, it is called now, named after the Dogger Bank, a shallow rise in the North Sea where fishing trawlers still drag up bones, mammoth tusks, aurochs skulls, lion teeth, and occasionally worked stone tools, harpoon points, fragments of a human world that existed when the land was dry and the water was somewhere else. Between 10,000 and 7,000 years ago, as the glaciers melted and the seas rose, Doggerland shrank, first into a series of low-lying islands, then into memory, then into nothing but seabed, buried beneath sediment, invisible, forgotten until the 20th century when fishermen began pulling up evidence that something had been there. It was not a wilderness. It was a heartland, a fertile plain connecting what would become England to what would become the European continent, crossed by rivers fed by glacial melt, dotted with forests and wetlands where hunter-gatherers thrived. The climate was temperate. The land was rich. There were herds of red deer, wild boar, aurochs. There were fish in the rivers. There were birds migrating through in uncountable numbers. And there were people, families, communities, cultures we will never know the names of because they left no written records, only stone tools and bone fragments scattered across a landscape now submerged beneath 60 feet of cold, murky water. When the ice melted, Doggerland drowned slowly. Not in a single flood, not in a single catastrophe, just the relentless, patient rise of water, year after year, generation after generation, claiming the low ground first, then the valleys, then the hills, then only the highest points remained as islands. Then those two vanished beneath the advancing North Sea. Around 8,200 years ago, a massive underwater landslide off the coast of Norway, the Storegga Slide, triggered a tsunami that swept across what remained of Doggerland, potentially accelerating its final submersion. Then the exact impact remains debated. What is not debated is the outcome. By 7,000 years ago, Doggerland was gone. The land bridge that had connected Britain to Europe for millennia was severed. Britain became an island. And the people who had lived there, if they survived, moved to higher ground, carrying forward what they could, leaving behind everything too heavy, too large, too fixed to the land to save. The North Sea now holds the largest well-preserved prehistoric archaeological landscape in the world. Not preserved in archives, not preserved in museums, preserved underwater, in silt and sand, waiting for sonar and seismic surveys and underwater drones to finally map the rivers, the coastlines, the settlements that once stood where fishing boats now trawl for cod and herring. Half a world away, another land drowned in the same slow catastrophe. Sundaland, a vast continental shelf connecting the Malay Peninsula, Sumatra, Java, and Borneo, was exposed during the last glacial maximum when sea levels sat 400 feet lower than today. It was not tundra. It was tropical, lush, warm, crossed by rivers that no longer exist, bordered by coastlines now submerged beneath the shallow waters of the Java Sea, the South China Sea, the Gulf of Thailand. There is evidence of savanna corridors cutting through the rainforest, open grasslands that would have allowed early humans and large mammals to move freely between the Asian mainland and the islands that are now isolated by water. Stable isotope analysis of bat guano and fossil mammal teeth confirms that the vegetation during the last glacial period was not the dense rainforest that dominates the region today, but something more open, mixed woodland and savanna, a landscape that supported megafauna, that supported human populations, that was habitable, traveled, known. When the ice melted, Sundaland disappeared. Not all at once. The rise of sea level during meltwater pulse 1A, around 14,600 to 14,300 years ago, was as much as 16 meters, over 50 feet, in just 300 years. For the people living there, This would have been catastrophic. Entire river valleys flooded. Coastal settlements drowned. Trade routes severed. Islands that had been connected became separated by widening straits that eventually became open ocean. The modern islands of Southeast Asia, Java, Sumatra, Borneo, are fragments of a much larger landmass. The shallow seas between them, less than 120 feet deep in most places, are not ancient ocean but drowned land, submerged plains that were walked, farmed, settled by people whose descendants now live on the remaining high ground, carrying forward oral traditions of a time when the world was larger, when the sea was farther away, when the ancestors lived in places that no longer exist. The stories persist, passed down through generations, tales of great floods, of lost lands, of cities swallowed by the sea. Scholars dismiss many of these as myth, as allegory, as cultural memory distorted by time. But the geology does not lie. The sea did rise, the land did drown, and the people who lived through it, if their stories survived, would have told exactly the kind of flood myths that appear in cultures all over the world, from Mesopotamia to the Pacific. The Mediterranean, too, holds its drowned history. Over 2,600 submerged archaeological sites have been documented across 19 nations bordering that ancient sea. Ports, temples, streets, harbors, entire cities now lying beneath the waves, some from earthquakes, some from subsidence, some simply from the slow, relentless rise of water that claimed coastlines built when the sea sat lower. Thonis Heraclean, a port city at the mouth of the Nile, flourished during the first millennium BC. It was Egypt's gateway to the Mediterranean, a bustling trade hub where Greek merchants met Egyptian priests, where ships from across the known world unloaded goods destined for the pharaoh's treasuries. Then, sometime in the 2nd century BC, the ground beneath the city became unstable. The Nile Delta is soft sediment, prone to liquefaction, prone to subsidence. The city sank, not destroyed, not burned, just slowly swallowed, settling into the seabed where it lay forgotten for 2,000 years until underwater archaeologists rediscovered it in 2000. The statues still stand underwater. The temples are still recognizable. The streets can still be walked, though now by divers, not citizens. Though the light that filters down is cold and green and carries no sound but the distant hum of boats passing overhead. The Cosquer Cave near Marseille, France, holds Paleolithic cave art, paintings of horses, bison, handprints, created 27,000 to 19,000 years ago when the cave entrance sat high above the Mediterranean. Now the entrance is 100 feet underwater, accessible only to technical divers, sealed off from casual exploration by the same rising sea that drowned Doggerland, that drowned Sundaland, that drowned coastlines all over the world during the final pulses of deglaciation. The art was not made underwater. It was made on dry land, in a cave that opened to a world where the Mediterranean coastline sat miles farther out, where the climate was colder, where glaciers still locked vast quantities of water and ice. The people who painted those walls did not know the sea would rise. They could not have imagined that their cave would one day be submerged, that their art would survive only because water sealed it away, preserving pigment in cold darkness where no air could erode it. The sea does not erase. It archives. Everything it takes, it holds in suspension, waiting for patient hands to rediscover what was thought lost. The Gulf of Khumbat sits off the western coast of India, a shallow bay where sediment from the Nirmada and Tapti rivers clouds the water year-round, making visibility nearly zero. It is not a place divers explore for pleasure. It is cold, murky, dark, the kind of water where you see nothing until your hand touches it. In December 2000, marine scientists from India's National Institute of Ocean Technology were conducting routine pollution surveys using side-scan sonar when the instruments began detecting something unexpected beneath the sediment. Geometrical structures, straight lines, right angles, features that do not occur naturally in riverbeds. Over a 9-kilometer stretch at depths between 20 and 40 meters, the sonar images revealed what appeared to be foundations, wall-like structures, and large rectangular forms partially buried under sand. Debris recovered from the site included pottery fragments, beads, sections of walls, and human bones. Some of the samples were subjected to carbon dating. The results came back as approximately 9,500 years old, if accurate, and that remains one of the largest ifs in modern archaeology. The site would predate the earliest known Indian civilizations by millennia. It would push urban settlement in the region back to a time when sea levels were still rising, when the coastline sat farther out, when the land now underwater was dry and possibly inhabited. The discovery was announced with considerable excitement by India's government in 2001. Comparisons were made to Harappan architecture, the Great Bath at Mohenjo-daro, the Acropolis at Harappa, structures known from sites dated to around 2600 BCE. But the Harappan civilization is only 4,500 years old. If the structures in the Gulf of Khumbat are truly 9,500 years old, they would represent something entirely different, an unknown culture, possibly wiped out or displaced by the rising seas at the end of the last ice age. The archaeological community responded with caution. The visibility in the Gulf is so poor that no diver has been able to visually confirm the structures. The sonar images are suggestive, but not conclusive. The carbon dating was performed on wood fragments, which could have come from anywhere, drifted in by rivers, deposited by currents, unrelated to any human settlement. Without clearer evidence, without excavation, without confirmation from multiple independent sources, the site remains controversial, debated, classified as possible, but unproven. Still, the sonar images exist. The geometrical patterns exist. And the Gulf sits in a region that was dry land during the last glacial maximum, when sea levels were lower and coastlines extended far beyond where they rest today. The sea took it. Whether it took a city, or only the memory of one, remains an open question. Half a world away, off the coast of Japan's Yonaguni Island, another underwater enigma sits in cold, clear water, visited by thousands of divers but understood by almost no one. The Yonaguni Monument, discovered in 1987 by a local dive instructor searching for new dive sites, is a massive stone formation approximately 50 meters long and 20 meters wide, sitting 25 meters below the surface. It looks carved. Terraced platforms, straight edges, steps that rise in parallel lines, flat surfaces that meet at near-perfect right angles. Some researchers believe it is man-made, the remnant of a structure built when sea levels were lower, possibly 10,000 years ago during the last ice age, when the Ryukyu Islands were still connected to the Asian mainland and the area around Yonaguni was dry land. Others argue it is entirely natural, a product of tectonic activity, erosion, and the geological processes that produce similar formations elsewhere in the world, like the Giant's Causeway in Northern Ireland. The debate has persisted for nearly 4 decades. Geologist Masaaki Kimura of the University of the Ryukyus spent years studying the site and concluded it showed clear signs of human modification, tool marks, quarried blocks, carved pathways. Most mainstream geologists disagree. They point out that the structure is part of a continuous rock mass, not separate blocks assembled by builders. They note that sandstone naturally fractures along planar surfaces when subjected to earthquakes and erosion, which are common in this seismically active region. But the angles are striking. The symmetry is unsettling. And the fact that the formation sits precisely at a depth consistent with sea level rise following the last glacial maximum makes it impossible to dismiss entirely. If it is natural, it is a remarkable coincidence. If it is not natural, then someone built it more than 10,000 years ago, in an age we do not associate with monumental architecture. Then the sea claimed it when the ice melted and the oceans rose. The monument does not argue its case. It simply sits there, 25 meters down, waiting for consensus that may never come. The Black Sea was once a lake. Not metaphorically. Literally. A freshwater lake, isolated from the Mediterranean by a land ridge across what is now the Bosporus Strait. During the last ice age, when sea levels dropped and glaciers locked water into ice, the connection between the Mediterranean and the Black Sea was severed. Rain and rivers filled the Black Sea basin, turning it into a vast inland lake, brackish, cold, home to freshwater species that adapted to the isolated environment. Then the ice melted. The Mediterranean refilled. And around 7,500 years ago, according to the hypothesis proposed by geologists William Ryan and Walter Pittman in 1997, the rising Mediterranean finally breached the land barrier at Bosporus. Salt water poured through the gap, an estimated 40 cubic kilometers per day, 200 times the flow of Niagara Falls, rapidly raising the level of the Black Sea by as much as 110 meters and flooding thousands of square kilometers of shoreline. The hypothesis gained widespread attention, not least because it seemed to align with flood myths recorded in various ancient cultures, including the biblical story of Noah. The idea was compelling. A sudden, catastrophic flood that displaced human populations living around the Black Sea, creating such a powerful collective trauma that the memory survived in oral tradition for millennia, eventually being written down as scripture. But subsequent research has challenged the hypothesis. In 2002, a team led by Ali Aksu of Memorial University of Newfoundland analyzed seismic profiles and sediment cores from the Bosporus Strait. They found evidence that fresh water was flowing out of the Black Sea into the Mediterranean at least 10,000 years ago, suggesting the Black Sea was already full and the saltwater intrusion was not a catastrophic flood but a gradual process. The debate continues. Some geologists still support the flood hypothesis. Others reject it. The physical evidence is ambiguous, capable of supporting multiple interpretations depending on which data is emphasized. What is not ambiguous is that the Black Sea rose, that coastlines were drowned, that settlements, if they existed along those ancient shores, were submerged beneath water that is now hundreds of feet deep. Whether it happened suddenly or gradually does not change the outcome. The land disappeared. The people who lived there had to leave. And the memory of that displacement, whether catastrophic or incremental, may have survived long enough to become myth, to become scripture, to become the foundation story of a culture that defined itself by what it had lost. The sea does not distinguish between sudden and slow. It only takes. And what it takes, it holds. There are more than 200 flood myths recorded across human cultures, from the Sumerian tale of Ziusadra, to the biblical Noah, to Manu in Hindu scripture, to Tata and Nina in Aztec tradition, to Yu the Great in Chinese legend. They appear in Mesopotamia, in the Americas, in India, in Greece, in the Pacific Islands. Some are remarkably similar. Others differ in every detail except the central event: water rising, land vanishing, survival contingent on building a vessel or fleeing to high ground. The oldest known version comes from Babylon, recorded by the historian Berosus around the 3rd century BCE, who referenced even older Sumerian texts dating to approximately 2900 BCE. In that telling, a king named Xisuthros is warned by a god of an impending deluge. He builds a ship, gathers his family and animals, and survives the flood by floating until the waters recede. After the rain ends, he releases birds to locate dry land, a motif that appears, nearly identical, in the later Epic of Gilgamesh and the biblical Genesis account. Some scholars argue these similarities prove a common origin, that the story began in Mesopotamia and spread outward as human populations migrated, carrying the myth with them, adapting it to new languages, new landscapes, new gods. But preserving the core narrative, a catastrophic flood, a chosen survivor, a vessel that saves the remnant. Others point out that many flood myths show no clear connection to the Mesopotamian template. The Chinese story of Yu the Great, for instance, does not involve a boat at all. Yu does not flee the flood. He stops it, draining the lowlands through engineering and determination, restoring order without divine intervention. The Hindu account of Manu involves a fish that warns of the coming waters and guides the boat to a mountaintop, a detail absent from the Sumerian versions. The Aztec myth involves a cypress tree, not an ark. And the warning comes from the god Tezcatlipoca, a figure with no parallel in Near Eastern mythology. These differences suggest independent origins, not one flood myth copied across continents. And multiple floods, multiple catastrophes, each culture recording its own experience of rising water, of displacement, of survival against a world that was rewriting itself. And the geology supports this interpretation, because the floods were real. Between 19,000 and 7,000 years ago, sea levels rose approximately 400 feet as the glaciers melted and released their locked water back into the oceans. This was not a single event. It was a series of pulses. Meltwater Pulse 1A around 14,600 years ago, Meltwater Pulse 1B around 11,500 years ago, each raising global sea levels by tens of feet in the span of a few centuries. For coastal populations, this would have been catastrophic. Not in a single day, not in a biblical 40 days and nights, but across generations, relentless, inexorable, the water advancing year after year until the old coastline, the old harbors, the old fishing grounds were gone, drowned, erased. Any culture living through that would have remembered. They would have told stories about it. Stories of elders who recalled when the shore was farther out, when the river mouth was wider, when the islands were still connected. Stories of fleeing inland, of abandoning settlements, of watching the sea claim what had been home. Oral traditions are not frivolous. They are archives. In cultures without writing, memory is preserved through narrative, through repetition, through ritual, through stories told and retold until they become fixed, stable, capable of transmitting information across centuries. Aboriginal Australians have oral traditions describing coastal landscapes that were drowned at least 7,000 years ago, and in some cases possibly as far back as 13,000 years, stories that align precisely with geological evidence of where the coastlines once sat. These are not vague myths. They are geographical records, passed down through 300 to 400 generations, preserved with such accuracy that modern geologists use them to reconstruct ancient shorelines. If Aboriginal cultures preserved such memories for 13,000 years, why not others? Why not the people who lived along the coasts of the Mediterranean, the Black Sea, the Persian Gulf, the coasts of India and Southeast Asia, all regions that experienced dramatic sea level rise during the post-glacial period? The flood myths are not metaphors. They are memories. Distorted by time, certainly. Encoded in religious language, yes. But at their core, they record what actually happened. The world drowned. And the people who survived told their children, who told their children, who told their children. Until the story became scripture, became myth, became the foundational narrative of cultures separated by oceans and millennia. The migrations that followed the floods reshaped the human world. As coastlines drowned and land bridges were severed, populations moved inland, moved to higher ground, moved away from the advancing water. The Bering Land Bridge, Beringia, which had connected Asia to North America for thousands of years, began to flood around 13,000 years ago. By 11,000 years ago, it was gone, replaced by the Bering Strait, cutting off the overland route and isolating populations on either side. Human dispersal into North America remains debated. But recent paleoenvironmental reconstructions suggest there were viable windows for coastal migration during the deglaciation, periods when sea levels were intermediate. But ice sheets had retreated enough to expose terrestrial corridors along the Pacific coast. But currents were less severe and sea ice less extensive. The most environmentally favorable periods appear to be 24,500 to 22,000 years ago, and again 16,400 to 14,800 years ago, narrow windows when conditions were benign enough to allow human movement by watercraft along the coast, hopping from one exposed shoreline to another, following the receding ice as it opened new land. By the time the glaciers had fully retreated, the coastlines had shifted hundreds of miles inland from where they had been during the last glacial maximum. Any settlements built during those earlier periods, any ports, any fishing villages, any coastal cultures that thrived when the land extended farther, were now underwater, buried beneath sediment, inaccessible except to submersibles and sonar. The maps that showed those coastlines became orphans. Accurate, precise, but depicting a world that no longer existed. Copied forward by cultures who could not verify them because the geography they recorded was drowned. And the myths became all that remained, stories of a time before the flood, when the world was larger, when the ancestors lived in places that are now only water, only memory, only the faint echo of something lost. Beneath 2 miles of ice lies a continent no human has ever fully seen. Not in its entirety, not in its true shape. Antarctica, the coldest, driest, most inhospitable place on Earth, is hidden. Its mountains are buried. Its valleys are filled with frozen water pressed, so dense it has become stone in all but chemistry. Its coastlines, its rivers, its lakes, all invisible, all archived beneath a glacial silence that has lasted millions of years. But the ice is not impenetrable. Radar can pierce it. Radio waves, transmitted from aircraft flying low over the wide expanse, penetrate the ice sheet and reflect back from the bedrock below, revealing a landscape that exists only in data, in false color images, in maps compiled from thousands of passes over terrain no eye will ever see unaided. What those maps show is not emptiness, not a flat, featureless plain. Antarctica beneath the ice is a world of extremes. Mountain ranges comparable to the Alps, canyons deeper than the Grand Canyon, valleys that would be spectacular if they were not entombed, invisible, known only to the instruments that measure the time it takes for radio waves to bounce off rock and return. The Gamburtsev Mountains sit buried under 2 to 3 kilometers of ice in East Antarctica, a range comparable in size to the European Alps, complete with peaks that rise over 3,000 meters above the surrounding bedrock, yet invisible from the surface, unmarked on any map made before the invention of radar. They were discovered in 1958 by Soviet geophysicists conducting seismic surveys. And their existence remains one of the strangest features of Antarctic geology, a mountain range sitting in the middle of a stable continental craton, far from any tectonic boundary, with no obvious explanation for why they are there or how they formed. Princess Elizabeth Land, in East Antarctica, holds what may be a canyon system stretching over 1,100 kilometers, longer than the Grand Canyon, carved into bedrock now buried under kilometers of ice, detectable only through radar imaging that reveals the depth and contour of the hidden terrain. And beneath it all, over 400 subglacial lakes, bodies of liquid water kept from freezing by geothermal heat rising from the Earth's core, insulated by miles of ice that prevent the warmth from escaping. The largest of these, Lake Vostok, is comparable in size to Lake Ontario, roughly 250 kilometers long and 50 kilometers wide, sitting beneath 4 kilometers of ice, isolated from the surface for at least 15 million years. Antarctica is not solid ice. It is a drowned continent, not drowned in water, but in frozen water. And what it holds beneath that ice is a record of what it once was, before the glaciers came, before the cold locked it in place, before it became the white void at the bottom of the world. 60 million years ago, Antarctica was green, not metaphorically, not in distant geological epochs before life existed. 60 million years ago, after the dinosaurs, after the asteroid impact, after the Cretaceous extinction event that reset the world, Antarctica sat where it sits now, over the South Pole. After it was not frozen, forests covered the continent. Subtropical vegetation grew in valleys where ice now sits miles thick. The climate was 20 degrees Celsius warmer than present. There were rivers. There were lakes. There were coastlines where waves broke on beaches that have not seen sunlight in millions of years. Glaciers existed even then, but only in the highest peaks of the transantarctic mountains. Small mountain glaciers, alpine ice, nothing like the continental ice sheet that dominates today. These were possibly the only glaciers on Earth at the time, isolated features in a world otherwise free of ice, relics of localized cold in a planet that was still recovering from the heat of the Mesozoic. Then the climate began to cool. Slowly at first. The Earth transitioned from a greenhouse state to an icehouse state, driven by shifts in atmospheric carbon dioxide, by changes in ocean circulation as continents drifted into new configurations, by the opening of the Drake Passage between South America and Antarctica around 30 million years ago, which allowed the Antarctic circumpolar current to form, a massive flow of water circling the continent, isolating it thermally from warmer equatorial currents, locking it into perpetual cold. By 34 million years ago, during the Eocene-Oligocene transition, the first permanent ice sheet formed on Antarctica. It started small. Mountain glaciers expanded, merged, spread outward from the high peaks until they covered the lowlands, until they reached the coasts, until the entire continent was buried beneath ice that would not melt again. For 15 million years, during the Miocene climatic optimum around 15 million years ago, the climate warmed slightly. Some researchers suggest the ice sheet may have partially retreated, that mountain glaciers may have reappeared in the highest peaks as the larger ice masses thinned. But the warming was temporary. The ice returned. And by the time the Pleistocene glaciations began 2 million years ago, Antarctica was locked in its current state. A frozen continent, isolated, inaccessible, its true landscape hidden beneath ice that has not retreated in millions of years. But the landscape is still there, preserved, waiting, held in suspension beneath the ice like a memory frozen mid-thought. The rivers are still there, frozen in time. Not the water itself, that is long gone, evaporated or locked into ice or drained into seas that no longer exist in the same form. But the channels remain. The valleys carved by ancient rivers, the deltas where water once spread into shallow seas, the subglacial pathways where meltwater still flows beneath miles of ice, following courses cut when Antarctica was green and the climate was warm. In 2024, a team of scientists using radar and satellite data discovered an ancient river landscape beneath East Antarctica, a network of channels, valleys, and flat erosional surfaces carved by rivers between 80 million and 34 million years ago, during the late Cretaceous and early Cenozoic periods when the continent was still forested and the ice had not yet formed. The landscape is remarkably preserved, flattened by millions of years of slow erosion as rivers meandered across low-lying plains, cutting into bedrock, depositing sediment, creating a topography that now sits invisible beneath 2 to 3 kilometers of ice. These ancient river systems are not mere curiosities. They influence how ice flows across Antarctica today. Modern glaciers follow the contours of the buried landscape, channeled by valleys carved millions of years ago, accelerating or slowing depending on the shape of the bedrock beneath them. The past is not static. It shapes the present, even when buried, even when invisible, even when forgotten by everything except the ice that slides over it. In the Ross Sea, off the coast of West Antarctica, researchers discovered a fossilized river system that was active as recently as 15,000 years ago, connected to subglacial lakes on the upstream end and to the ice margin on the downstream end, a complete hydrological network preserved in the sediment of the deglaciated seafloor. The river was massive, fed by meltwater from retreating ice sheets during the warming period that followed the last glacial maximum, carving channels into the bedrock as the glaciers pulled back. The fossilized channels show exactly how the ice retreated, not in a straight line, but in a U-turn, following the course of the subglacial river, reversing direction multiple times as the ice stream tracked the path of water flowing beneath it. It is the only documented example on the Antarctic seafloor where a single ice stream completely reversed its retreat direction to follow a subglacial hydrological system. Another ancient river system, discovered through sediment cores drilled from the West Antarctic ice sheet, dates to approximately 40 million years ago during the Eocene epoch, when Antarctica was still warm and forested. The river stretched nearly 1,500 kilometers from the Transantarctic Mountains to the Amundsen Sea, a distance comparable to the length of the Mississippi River, draining vast tracts of land that are now buried beneath ice. The sediment cores contained lipid biomarkers, organic molecules from cyanobacteria that live only in freshwater, confirming that the deposits were laid down by a river, not by ocean currents or glacial melt. The grains were traced to a salt region in the Transantarctic Mountains, meaning the river crossed nearly the entire continent before emptying into the sea. That river is gone now. Its valley is filled with ice. But the memory of it remains, encoded in sediment layers thousands of meters below the surface, waiting for drills to retrieve it, for laboratories to analyze it, for scientists to reconstruct the shape of a world that has not existed for 40 million years. The ice itself is a library. Each layer holds a year, sometimes more, sometimes less, depending on how much snow fell, how much wind scoured the surface, how the ice compacted over time. Deeper layers are older, compressed under the weight of everything above them, thinned but not destroyed, preserving air bubbles from ancient atmospheres, isotopes from ancient temperatures, ash from ancient volcanoes. In January 2025, the Beyond Epica project completed drilling an ice core 2,800 meters deep at Little Dome Sea in East Antarctica. reaching bedrock, retrieving ice that is over 1.2 million years old, possibly older, extending the continuous climate record further back than any ice core ever drilled. The ice contains trapped air bubbles, microscopic pockets of atmosphere sealed into the ice as it formed, preserved without contamination for over 1 million years. By analyzing the composition of those bubbles, scientists can measure past concentrations of carbon dioxide, methane, and other greenhouse gases, tracking how the atmosphere has changed across glacial and interglacial cycles, across ice ages and warm periods, across epochs when the planet looked nothing like it does today. The deeper they drill, the older the ice, the farther back the record extends. At 1.2 million years, the ice captures a critical transition in Earth's climate, the shift from 41,000-year glacial cycles to 100,000-year cycles, a change that fundamentally altered how ice ages begin and end, how much ice accumulates, how long it lasts before melting. Why the shift occurred remains unknown. The ice may hold the answer, or it may only deepen the mystery, revealing patterns that suggest causes we have not yet imagined. The drilling took place at an altitude of 3,200 meters above sea level, in temperatures averaging -35 degrees Celsius during the summer, in conditions so harsh that sustained work required years of preparation, multiple field seasons, and a team willing to endure isolation, cold, and the endless white silence of the Antarctic plateau. But the ice core is now retrieved. The data is being analyzed. And for the first time, humanity has access to a continuous climate record stretching back over 1 million years, a window into Earth's past that extends far beyond the reach of written history, beyond the reach of archaeology, beyond the reach of anything except the ice itself, which has been patiently archiving every breath the planet took for longer than our species has existed. The ice is not eternal. It holds, patient and vast, covering 98% of Antarctica's surface, averaging 2 kilometers thick, reaching depths of over 4 kilometers in East Antarctica's interior. But it has melted before, and it will melt again, not in centuries, perhaps, but in the slow arithmetic of geological time. It is not permanent. It is conditional, dependent on climate, on ocean currents, on atmospheric carbon dioxide levels that regulate how much heat the planet holds, how much ice can survive. During the early to middle Holocene, between 9,000 and 5,000 years ago, parts of the East Antarctic ice sheet experienced rapid thinning. In coastal drowning Maud Land, the ice sheet retreated over 100 kilometers inland, driven by a combination of rising sea levels and warmer ocean waters that flowed beneath the ice shelves, melting them from below, destabilizing the grounding line where ice transitions from resting on bedrock to floating on the sea. The deglaciation was not caused by atmospheric warming alone. Regional sea levels rose higher than today, possibly 15 to 20 meters higher by around 9,000 to 8,000 years ago, due to glacial isostatic adjustment, the slow rebound of land that had been compressed under ice during the last glacial maximum. The higher sea levels increased ice shelf buoyancy, lifting the shelves off their grounding points, allowing warm circumpolar deep water to flow beneath them and accelerate basal melting. The ice thinned rapidly. Coastal margins retreated. And for a few thousand years, portions of Antarctica's edge were less stable than they are today, more exposed, more vulnerable to the warming ocean. Then, during the mid to late Holocene, the ice began to readvance. Sea levels fell slightly as water was redistributed globally. The climate cooled. Ice shelves regrew, and glaciers pushed back toward the coast, reoccupying ground they had abandoned centuries earlier. By the late Holocene, roughly 2,000 years ago, the Antarctic ice sheet had returned to near its present-day configuration. Though some regions continued to lose or gain ice into the industrial era, the ice is dynamic. It breathes. It advances and retreats in response to forces that operate across millennia. Ocean temperatures, sea level changes, atmospheric carbon dioxide, the shape of the bedrock beneath it. It is not a static frozen monument. It is a living system, slow-moving but alive, responding to the planet's climate in ways we are only beginning to understand. And under sustained warming, under the climate scenarios projected for the coming centuries, much of it may not survive. Under a high-emission scenario, where global temperatures rise by 4.5 degrees Celsius above pre-industrial levels, up to 60 of Antarctica's ice shelves could become non-viable by the year 2300. Non-viable does not mean they disappear overnight. It means they cross a threshold beyond which they cannot maintain their current structure, where melting from below exceeds the rate at which new ice flows in from above, where thinning accelerates until the shelf collapses entirely, breaking into icebergs that drift into open ocean and melt. When an ice shelf collapses, the glaciers behind it accelerate. The shelf acts as a buttress, holding back the flow of land ice toward the sea. Remove the buttress, and the glacier speeds up, thinning, calving more rapidly, contributing more directly to sea level rise. The collapse of the Larsen B ice shelf in 2002 demonstrated this. Within months of the shelf's disintegration, the glaciers that had been feeding it accelerated by a factor of 2 to 8, discharging ice into the ocean at rates never before observed in that region. The pattern has since been documented at other collapsing shelves, Thwaites, Pine Island, Wilkins. Each loss weakens the system. Each collapse unlocks more land ice. Each acceleration pushes sea levels higher. If 60 of Antarctica's ice shelves fail, the resulting sea level rise could reach 10 meters, roughly 33 feet, enough to drown major coastal cities, to redraw coastlines, to displace hundreds of millions of people. That outcome is not imminent. It lies centuries in the future, contingent on whether emissions continue unabated or are reduced. But the threshold exists, and once crossed, the process may be irreversible, not on human timescales, but on the timescales that matter to ice, which measures change in millennia, not election cycles. The key threshold for long-term ice sheet stability appears to lie between 1.5 and 2 degrees Celsius of warming above pre-industrial levels. Beyond that, individual ice shelves, Ross, Ron Filchner, the major drainage basins that hold back vast quantities of inland ice, begin to destabilize. And the contributions to sea level rise escalate from manageable to catastrophic. The window is narrow, and it is closing. The maps showed Antarctica without ice. Not all of it, not the deep interior, but the coasts, Queen Maud Land, the mountain ranges, the river valleys that are now buried beneath glaciers 2 miles thick. Whether those maps are accurate remains contested. Some researchers argue that the coastline depicted on the Piri Reis map matches seismic surveys of Queen Maud Land with remarkable precision, showing features that would only be visible if the ice were absent. Others counter that the comparison is flawed, that the bedrock topography beneath Queen Maud Land was largely unmapped until the 1970s, that any resemblance between the map and the subglacial landscape is coincidental or exaggerated. The American Geophysical Union published research in 1995 demonstrating that Antarctica has been ice-covered for at least 14 million years, too long for any human cartographer to have seen it ice-free and recorded the coastline. If that conclusion is accurate, then the maps cannot show what they appear to show. They must depict something else. South America distorted by projection errors, artistic invention, geographic features misidentified by later interpreters eager to find evidence of lost civilizations. But the maps exist, and they are precise, not vaguely suggestive. Precise. Latitudes that align. Mountain ranges that match. Coastlines that, when overlaid on modern seismic data, correspond with an accuracy that should not be possible if the cartographers were guessing. The debate will not resolve easily. Both sides hold evidence. Both sides make compelling arguments. And the ice, silent, patient, hiding the truth beneath 2 miles of frozen water, offers no testimony that either side can verify without melting it, which we are now doing, slowly, inadvertently. As the climate warms and the planet begins to exhale what it has held frozen for so long, perhaps in a few centuries, when the ice has retreated enough, we will finally see Antarctica as it was drawn, not as myth, not as speculation, when as coastline, visible, verifiable, undeniable. And then the question will no longer be, could someone have mapped this? It will be, how did they know? If the maps are real, if they record coastlines that existed before the ice claimed them, then someone made them. Not gods, not visitors from distant stars. People, sailors who understood the pull of tides, the turn of constellations, the way wind bends around distant islands. Navigators who cross seas without instruments we consider essential, who mapped shorelines without satellites, who recorded the world as it was, not as we imagine it, but as it actually looked during a climatic window we barely understand. They would have been maritime cultures, not empires with monuments and written histories, not centralized states that built temples meant to last millennia, but networks, loose, dispersed, connected by trade and knowledge rather than borders and armies. People who lived on coasts, who built boats from cedar and pine, who understood that survival meant movement, adaptation, the willingness to sail toward horizons that promised food, shelter, new land when the old land drowned. The Phoenicians offer a template, though they came much later. Between 1550 and 300 BCE, they sailed from the cities of Tyre, Sidon, and Byblos, establishing trade networks that stretched from the Levant to the Atlantic coast of Iberia, from Cyprus to the British Isles. They did not conquer. They traded. They moved goods, timber, purple dye, glassware, metals, across distances that required precise navigation, knowledge of currents and winds, the ability to return home after voyages that lasted months. Their ships were not primitive. They were engineered, cedar frames, planking held with nails and rope lashings, shallow draft hulls that could sail close to shore without running aground, yet sturdy enough to cross open ocean. Archaeological reconstructions of 8th century BCE Phoenician trading vessels show designs that allowed efficient maneuvering even when loaded with cargo, demonstrating an advanced understanding of naval architecture that took generations to develop. They navigated by the stars. During the day, they oriented by the sun. At night, they used Polaris, what they called Wab, the Stella Phoenica, the Phoenician star, to determine latitude. They understood celestial navigation, measuring the angle between stars, calculating position based on their height above the horizon, using dead reckoning to estimate speed and direction when clouds obscured the sky. This knowledge was not written down for centuries. It lived in practice, in oral tradition, passed from sailor to sailor, from father to son, from one generation to the next, until eventually it was codified in texts that have since been lost or survive only in fragments copied by later scholars who no longer understood the mathematics behind them. The Phoenicians were not the first. They inherited their maritime knowledge from earlier cultures, the Minoans, the Egyptians, possibly others whose names have not survived. The technology, the navigational techniques, the understanding of how to cross open ocean and return home. These did not appear fully formed in the second millennium BCE. They developed over thousands of years, refined through trial and error, through voyages that succeeded and voyages that did not, through the slow accumulation of knowledge that becomes tradition, becomes survival, becomes the foundation on which civilizations are built. During the last glacial maximum, when sea levels sat 400 feet lower than today, the coastlines looked different. Land bridges connected continents. Islands that are now scattered were once continuous landscapes. The Pacific coast of North America extended miles farther west, exposing continental shelf that is now submerged. People lived along those coasts. Not in great cities, there is no evidence of that, but in settlements, camps, fishing villages, places where resources were abundant enough to support stable populations. They hunted marine mammals. They fished. They gathered shellfish. They built boats, not complex vessels, perhaps, but watercraft capable of navigating coastal waters, of traveling between islands, of crossing straits when migration required it. The evidence for this comes not from monuments, but from middens, refuse heaps containing shells, fish bones, tools, and from genetic data showing that human populations moved along coastlines, not just through interior corridors, during the last ice age. The timing of migration into the Americas, the routes taken, the technologies employed, all of this remains debated. But the coastal migration hypothesis, bolstered by paleo-environmental reconstructions, suggests that maritime cultures were active along the Pacific Rim between 25,000 and 14,000 years ago, during periods when sea ice provided seasonal platforms for winter travel and open water allowed summer navigation. Watercraft technology existed in Southeast Asia by at least 40,000 years ago, evidenced by dietary remains in Indonesian middens showing offshore fishing, activity that requires boats capable of reaching waters beyond swimming distance from shore. By 13,000 years ago, watercraft were being used in Japan, in the Ryukyu Islands, in the island chains off the coast of East Asia where maritime cultures moved freely between land masses now separated by ocean. These were not primitive rafts. They were seaworthy vessels, capable of carrying people and cargo across distances that required planning, knowledge, the ability to navigate by stars and currents, and the flight patterns of seabirds returning to land. If such cultures existed in the Pacific 40,000 years ago, what else was possible? What other coastlines did they sail? What other lands did they map before the ice melted and the seas rose, and the geography they knew disappeared beneath water? The Polynesians crossed the Pacific without instruments. No compass, no sextant, no charts in the way we understand them. They navigated by stars, by swells, by the flight of seabirds, by the color of water and the shape of clouds forming over distant islands they could not yet see. The Hawaiian star compass divides the horizon into 32 houses, rising and setting points for hundreds of stars, memorized by master navigators who spent lifetimes learning which stars rose in which house, which paths they followed across the sky, which destinations could be reached by steering towards specific constellations. The system is not abstract. It is practical, tested across thousands of miles of open ocean, refined through generations of voyages where mistakes meant death and success meant survival. The navigator does not steer by looking at a map. The navigator is the map. The knowledge lives in memory, in the body's sense of the canoe's motion as it rides swells generated by storms hundreds of miles away, in the ability to read subtle patterns in wave direction and height that reveal the presence of land beyond the horizon. Swells bend around islands, refract, interfere with each other in ways that create detectable patterns. A skilled navigator can feel these patterns through the hull, can determine the direction to land by reading the rhythm of waves, the cadence of how water moves when something solid disrupts its flow. Seabirds are another compass. Certain species nest on land and fly out to sea during the day to feed, returning to shore at dusk. If you see terns flying in a consistent direction as the sun sets, land lies that way, even if it is still below the horizon. Clouds gather over islands, forming stationary formations in otherwise moving skies. Reflected light from shallow lagoons tints the underside of clouds a pale green, detectable from 30 miles away if you know what to look for. This is not primitive navigation. This is science. Observation, pattern recognition, hypothesis testing across lifetimes, across cultures, across an ocean so vast that finding a small island within it should be impossible, but was accomplished routinely by people who memorized the stars, who learned to read water, who passed their knowledge forward through oral tradition so precise that modern reconstructions using traditional methods have successfully replicated ancient voyages. The Kli, a Polynesian voyaging canoe, has sailed from Hawaii to Tahiti and back multiple times using only traditional wayfinding. No GPS, no compass, no modern instruments, proving that the ancient methods work, that the knowledge was real, that what oral tradition preserved was not myth, but maritime science encoded in narrative, in chant, in the careful teaching of elders who understood that memory is the only chart that cannot be lost at sea. If the Polynesians could navigate the Pacific 1,000 years ago, what was possible 10,000 years ago? What other maritime cultures, in other oceans, developed similar systems, star compasses, wave reading, seabird navigation, that allowed them to sail coastlines we no longer have access to because those coastlines are drowned? Oral tradition is not fragile. It is engineered for durability. Stories, songs, chants, these are mnemonic devices structured to be memorable, repeated across generations in forms that resist corruption. Aboriginal Australians have oral traditions describing coastal landscapes submerged 7,000 to 13,000 years ago, stories that align with geological data showing where the coastlines once sat. These are not vague myths. They are geographical records, transmitted through 300 to 400 generations with accuracy sufficient to reconstruct ancient shorelines. Pacific Island communities use chants that describe ocean currents, star patterns, fish aggregation sites, oral maps that have proven remarkably accurate when compared with modern scientific data. The precision is not accidental. It is the result of deliberate pedagogy, of elders teaching younger generations through repetition, through ritual, through the kind of structured learning that ensures critical knowledge survives even when no written record exists. In cultures without writing, memory is the archive. And memory, when trained, when reinforced through ceremony and practice, is capable of preserving information across timescales that exceed the lifespan of empires, of written languages, of monuments that crumble while the story remains intact. If Aboriginal cultures preserved geographical knowledge for 13,000 years, when Polynesian navigational knowledge survived centuries of oral transmission before being written down, when what other knowledge might have survived in similar fashion? What other maps, drawn during warmer climatic periods when coastlines were different, might have been encoded in oral tradition, copied onto parchment centuries later by scribes who no longer understood the geography they were recording, but preserved it nonetheless because the knowledge had value, because it came from sources they respected, because it was part of a tradition older than their own? By the Bronze Age, maritime trade networks connected the Mediterranean from Egypt to the Aegean, from the Levant to Anatolia, from Crete to the coasts of Syria and Cyprus. Minoan Crete served as a hub, exporting pottery, olive oil, textiles, luxury goods across routes that required precise navigation, knowledge of seasonal winds, the ability to return home after voyages lasting weeks or months. The Mycenaeans expanded these networks, trading copper, tin, gold, raw materials sourced from distant regions and transported by ship across open water. Shipwrecks from this period, like the Yalubaran wreck off the coast of Turkey, dated to approximately 1300 BC, reveal cargoes of copper ingots, tin, glass, ivory, resins, luxury items from a dozen different cultures, all carried on a single vessel that sank while traveling a well-known trade route. These were not exploratory voyages. These were routine trade runs, repeated seasonally, following routes that had been sailed for centuries, using navigational knowledge passed from captain to captain, encoded in sailing directions that described landmarks, currents, harbors, dangers, information too valuable to lose, too critical for survival to be left unrecorded. Some of that knowledge was written down. Much of it was not. And when civilizations collapsed, when the Bronze Age ended in catastrophe around 1200 BCE, when trade networks disintegrated, when cities burned and populations migrated, much of the accumulated navigational knowledge was lost. But not all of it. Some survived, copied by later cultures, preserved in fragments, passed forward through channels we can no longer fully trace, until it emerged centuries later in the hands of Ottoman admirals and Renaissance cartographers who no longer understood what they were copying, but copied it anyway. Until the maps were old, until they came from respected sources, until the lines, until impossible, were too precise to ignore. Ice is not silent. It speaks in layers, in isotopes, in bubbles of trapped air that hold the breath of ancient atmospheres. Every snowfall that settled onto Antarctica, every season that passed, every year that accumulated, all of it is archived, compressed into the ice sheet, waiting for drills to retrieve it, for laboratories to decode it, for scientists to read the planet's history in frozen water that has not melted in hundreds of thousands of years. An ice core is a time machine. Not metaphorically, literally. Each meter of ice corresponds to years or decades of accumulation, depending on how much snow falls at the drilling site. Near the surface, the layers are distinct, light snow alternating with wind-compacted layers, seasonal variations visible to the eye. Deeper down, the layers thin as the weight of ice above compresses them, squeezing out air, turning snow into glacial ice so dense it barely resembles the powder that once fell from the sky. But the air remains. Tiny bubbles, sealed into the ice as it compacted, preserve samples of the atmosphere from the year the snow fell. Snapshots of carbon dioxide, methane, oxygen, nitrogen, trapped and unchanging, insulated from the modern world by miles of ice. By analyzing the composition of those bubbles, scientists can measure greenhouse gas concentrations across glacial and interglacial cycles, across ice ages and warm periods, across epochs when the climate looked nothing like it does today. The longest continuous ice core, drilled at Dome C in East Antarctica, reaches back 800,000 years. 8 glacial cycles, 8 ice ages, and 8 interglacials, each recorded in the ice, each revealing how the climate shifted, how temperatures rose and fell, how the planet breathed across timescales so vast that human history becomes a footnote, a thin layer at the very top of the core, barely distinguishable from the snow that fell last year. And now, with the Beyond Epica core completed in January 2025, the record extends past 1.2 million years, reaching a critical transition in Earth's climate when glacial cycles changed from 41,000-year rhythms to 100,000-year rhythms, a shift that fundamentally altered how ice ages begin and end, how much ice accumulates, how long it lasts before melting. The ice remembers. It holds every volcanic eruption, every forest fire, every shift in ocean circulation, every change in solar radiation, all of it encoded in layers that wait, patient and cold, for the instruments that can finally translate their silent archive into knowledge. But ice cores are not the only archive. The seafloor holds its own records, sediment cores drilled from the ocean floor around Antarctica, capturing millions of years of history in layers of mud, sand, microfossils, and stones carried by icebergs from the retreating continent. The Andril Project, Antarctic geological drilling, extracted 2 sediment cores from the Ross Sea between 2006 and 2007, each over 1,200 meters long, together providing an almost uninterrupted 17-million-year record of Antarctica's climatic past. Where ice cores stop at 800,000 years, or now 1.2 million, sediment cores continue backward through the Pliocene, through the Miocene, through epochs when Antarctica was not frozen. When forests grew where ice now sits miles thick, the sediments reveal warm periods, prolonged ice-free phases, times when the West Antarctic ice sheet collapsed entirely, raising global sea levels by up to 10 meters, flooding coastlines, rewriting geography in ways we are only beginning to understand. One such warm period occurred around 3.5 million years ago, during the Pliocene, when atmospheric carbon dioxide levels were similar to those we are approaching today, around 400 parts per million, and temperatures were 3 to 4 degrees Celsius warmer. For 200,000 years during that period, the West Antarctic ice sheet may have disappeared completely. Not thinned, not retreated slightly. Gone. The land beneath it exposed, the rivers flowing, the coastlines free of ice. Then the climate cooled again, and the ice returned, rebuilding over millennia until it reached the configuration we see today. A configuration that, according to the sediment cores, is not permanent but conditional, dependent on temperatures that, and they rise by just a few degrees, could trigger another collapse. 16 million years ago, during the Miocene climatic optimum, Antarctica had a climate similar to present-day New Zealand, temperate, forested, crossed by rivers, warm enough to support vegetation and possibly animal life. Pollen grains, preserved in the sediment cores, confirm the presence of forests. Microfossils indicate warm ocean temperatures. Mineral grains traced to specific rock formations on the continent show that rivers were carving valleys, transporting sediment to the sea, shaping a landscape that no longer exists except as data, as cores, as the faint memory of a world erased by ice. The record is clear. Antarctica has not always been frozen, and the ice that covers it now is not invincible. It has melted before, completely, and it could melt again. The fossils tell a story the ice cannot erase. In the Transantarctic Mountains, in the sandstone cliffs of Alexander Island, in the exposed rocks of the Antarctic Peninsula, fossils lie preserved in stone. Leaves pressed flat by time would turn to mineral, pollen grains so ancient they predate the ice by millions of years. These are not relics of a distant planet. They are Earth's own memory, archived in rock, holding the shape of forests that once grew where glaciers now sit miles thick. 90 million years ago, during the Cretaceous period, Antarctica was covered in temperate rainforest, swampy, warm, crossed by rivers that drained into shallow seas. The climate was 20 to 25 degrees Celsius warmer than today. Carbon dioxide levels were 4 to 6 times higher than pre-industrial concentrations. And the South Pole, though tilted and dark for months at a time during winter, supported lush vegetation. Ferns, mosses, conifers, flowering plants including the earliest ancestors of the southern beech, Nothofagus, which still grows in New Zealand and Tasmania today. In 2017, researchers drilling in the Amundsen Sea, near the Pine Island and Thwaites glaciers, extracted a sediment core from the seafloor. When they CT scanned it, they found something extraordinary. Pristine forest soil, complete with root systems, pollen, spores, and organic matter so well preserved that individual plant cells could be identified. The sediment was 90 million years old, laid down on land, not in the ocean. Then buried as the ice advanced, and the continent transformed from green to white over millions of years. The pollen grains confirmed the presence of flowering plants, angiosperms, at latitudes closer to the South Pole than had been documented before. The soil contained layers of organic matter thick enough to suggest a dense forest, possibly with canopy heights comparable to modern temperate rainforests. The roots were intact, frozen in place, holding the shape of trees that once stood tall before the ice came and buried them beneath 2 miles of frozen water. The forest is gone now, but the memory remains, encoded in sediment, in fossils, in layers of ancient soil that hold the breath of a world that existed long before humans, that knew nothing of ice, that thrived under a climate so different from the present that it barely seems like the same planet. 250 million years ago, during the early Triassic, Antarctica was part of Pangaea, the supercontinent that held all of Earth's land masses in a single connected mass. The continent sat largely within the Antarctic Circle, experiencing extended periods of darkness each winter, just as it does today. But it was not frozen, and it was inhabited. Fossils of Lystrosaurus, a four-legged, mammal-like reptile about the size of a pig, have been found in Antarctic rocks dating to this period. The creature was a survivor, having lived through the Permian-Triassic extinction event, the worst mass extinction in Earth's history, which wiped out 70 of vertebrate species on land. Lystrosaurus not only survived but thrived, spreading across Pangaea, adapting to a wide range of climates from tropical to polar. Analysis of fossilized tusks suggests that Antarctic Lystrosaurus may have entered a hibernation-like state to survive the long, dark winters. Growth rings in the tusks show irregular patterns consistent with torpor, a metabolic slowdown that allows animals to survive periods when food is scarce and temperatures drop. If true, this would be the oldest evidence of hibernation in the fossil record, predating mammals and dinosaurs, suggesting that the adaptation to extreme seasonal climates has a history stretching back 250 million years. The fossils are evidence, not speculation, not myth. Evidence that Antarctica has hosted life, abundant, diverse, resilient life, across geological epochs when the climate was warm enough to support forests, rivers, animals that walked on land now buried beneath ice that will not melt for millennia unless the climate changes in ways we are only beginning to anticipate. The ice sheet is not static. It is moving, thinning, responding in real time to changes in ocean temperature, atmospheric circulation, and the amount of greenhouse gases warming the planet. Between 1992 and 2020, the Greenland and Antarctic ice sheets lost a combined 7,560 billion tons of ice, enough to raise global sea levels by 21 millimeters. The rate of loss has accelerated, rising from 105 billion tons per year in the early 1990s to 372 billion tons per year between 2016 and 2020. Antarctica alone is losing approximately 135 billion tons of ice per year, with most of the loss concentrated in West Antarctica. where glaciers like Thwaites and Pine Island are thinning rapidly as warm ocean water flows beneath their ice shelves, melting them from below. The process is not uniform. Some regions are gaining ice, accumulating more snow than they lose to melting or calving. But the overall trend is clear: the ice is retreating. Glacial isostatic adjustment, the slow rebound of land that was compressed under ice during the last glacial maximum, complicates the measurements. As ice melts and the weight decreases, the bedrock beneath it rises, a process that can take thousands of years to complete. GPS stations across Antarctica record this uplift, measuring rates of a few millimeters per year in most places, but faster in regions where ice loss is accelerating. The models that predict future ice loss must account for this rebound, for the viscosity of the mantle beneath Antarctica, for the way the solid Earth responds to changing ice loads over timescales that span centuries to millennia. The uncertainties are large. The predictions vary depending on which Earth model is used, which ice sheet history is assumed, which climate scenario is projected. But the direction is not uncertain. The ice is melting. The coastlines will change. And the world that emerges, if the warming continues, if the ice retreats far enough, will look more like the Antarctica of the sediment cores, the Antarctica of the fossils, the Antarctica that existed before the ice came and buried everything. Whether that world will be mapped, whether anyone will be there to chart its rivers and mountains when they finally emerge from beneath the glaciers, remains an open question. But the ice remembers. And when it melts, the memory will resurface, not as myth, not as speculation, but as coastline, but geography, but the shape of a continent that has been waiting, patient and silent, to be seen again. The ocean has a memory longer than stone. Sediment settles in layers, year after year, century after century. The debris of continents washing into the sea, the shells of microscopic organisms drifting down from sunlit waters, the ash of distant volcanoes falling like snow across the surface and sinking into darkness. Each layer is a page. Each core drilled from the seafloor is a book. Millions of years compressed into cylinders of mud and sand, holding within them the chemical fingerprints of ancient climates, ancient oceans, ancient atmospheres that have not existed for epochs. The sediments do not forget. They archive everything. Temperature, encoded in oxygen isotopes trapped in foraminiferous shells. Carbon dioxide levels, recorded in the calcium carbonate deposited by plankton. Ice volume, inferred from the ratio of heavy to light oxygen that shifts depending on how much water is locked in glaciers versus flowing in the sea. The archive is not written in language. It is written in chemistry, in the slow accumulation of particles too small to see, but precise enough, when measured in laboratories, to reconstruct climates that existed 66 million years ago, when dinosaurs still walked the Earth and Antarctica was green. The Southern Ocean, surrounding Antarctica, holds sediment cores that reveal methane releases from the seafloor 23 million years ago, events that may have triggered regional or global climate changes, that may have warmed the planet enough to melt ice, to shift ocean currents, to rewrite the climate in ways we are only beginning to understand. The sediments remember. They hold the memory of a planet in flux, of ice sheets that grew and shrank, of coastlines that drowned and reemerged, of life that thrived and died and left behind only its shells, settling into the deep, waiting for instruments that could finally read what they had preserved. At 7.5 kilometers below the surface, in the Japan Trench, one of the deepest places on Earth, organisms burrow through sediment deposited by gravity flows that sweep material down from the trench margins above. These deep-sea dwellers engineer their own environments, reworking the seafloor, feeding on microbial communities, leaving traces in the sediment, burrows, tracks, disturbances that record behavior, that archive ecosystems we have barely begun to study. Even at depths where light has never reached, where pressure would crush a human instantly, life persists. And it leaves its mark, layered into the sediment like handwriting in a language we are only now learning to read. The ocean does not erase. It archives. And what it takes, it holds in suspension, not lost, not destroyed, but preserved in cold darkness, waiting for the patient hands of science to retrieve it, to decode it, to understand what it means. When the ice melted and the seas rose 400 feet, the coastlines drowned. The ports, the harbors, the fishing villages, the settlements that had existed for thousands of years along shores that are now submerged, all of them claimed by water that does not mourn, that does not remember names, that simply reclaims what gravity and time dictate belongs beneath the surface. But the sea does not destroy everything it takes. In some cases, it preserves. Underwater, away from oxygen, away from the bacteria that decompose wood and fabric and organic material, archaeological sites reach a state of equilibrium with their environment. The cold water, the sediment that covers them, the absence of air, all of this slows deterioration, allowing shipwrecks to remain intact for centuries, allowing streets and buildings to stand submerged but recognizable, allowing artifacts to survive in conditions that would have destroyed them on land. Thonis Heraclean, the Egyptian port city that sank beneath the Mediterranean 2,000 years ago, is better preserved underwater than many terrestrial sites of the same age. The statues are intact. The temples are recognizable. The streets can still be walked, though now by divers in wetsuits, not by merchants carrying goods from distant lands. The underwater environment sealed it, protected it, held it in suspension until technology advanced enough to rediscover it, to map it, to understand what it was before the sea claimed it. Across the Mediterranean, 2,600 submerged archaeological sites have been documented, shipwrecks, ports, entire cities, lying beneath water that rose as the glaciers melted, as the climate warmed, as the world transitioned from ice age to the interglacial period we still inhabit. Some sank due to earthquakes, some due to subsidence, some simply because the sea level rose and the land they stood on became coastline, then shallows, then open water. By 2100, 47 of the 49 UNESCO World Heritage Sites along Mediterranean coastlines are projected to be threatened by coastal flooding or erosion due to continued sea level rise. Venice, Alexandria, Carthage, the island of Delos, all of them face inundation, not in geological time, but in human time, within the lifetimes of people alive today. The Mediterranean has risen 2.8 millimeters per year over the past 30 years, a pace faster than the 20th century average. And projections suggest it could rise 90 centimeters above the year 2000 level by the end of this century. The cultural heritage of past civilizations, Phoenician, Greek, Egyptian, Roman, Byzantine, survived for millennia. It withstood wars, conquests, the rise and fall of empires. But it may not survive the climate, not because it is fragile, but because the sea is patient. And when it rises, it takes everything below the waterline, not violently, not suddenly, but inevitably, the way it has taken coastlines for 12,000 years, the way it took Doggerland, the way it took Sundaland, the way it will take whatever lies in its path, when the ice melts and the water rises and the world redraws itself once again. The coast is eroding, not slowly, not imperceptibly, but at rates that archaeologists can measure, that coastal managers can track, that communities living along shorelines can see within their own lifetimes. Climate change is accelerating the loss. Rising sea levels, increasing storm intensity, coastal erosion amplified by warming temperatures, all of it converging on archaeological sites that have survived for thousands of years but may not survive the next century. In the Middle East and North Africa, initial assessments suggest that up to 34 of documented coastal archaeological sites could have already experienced flooding, erosion, or storm damage. By 2050, sea level rise and extreme sea level events could impact 14 to 25 of sites. By 2100, that figure rises to 18 to 34. Coastal erosion projections are even more severe. Over 30 to 40 of archaeological sites in the region could be impacted by erosion by 2050, and potentially more than 40 by 2100 if carbon emissions remain high. These are not abstract threats. These are shell middens, ancient harbors, Phoenician ports, Roman villas, settlements that record 10,000 years of human interaction with the sea, all of it at risk of being claimed by the same water that drowned Doggerland, that submerged Sundaland, that has been rising since the ice began to melt 19,000 years ago. In California, along the Channel Islands, researchers have assessed the vulnerability of coastal shell middens, archaeological sites containing the remains of fish and shellfish that indigenous peoples harvested over 13,000 years. The middens are not just cultural artifacts. They are scientific archives, holding isotopic records of past sea surface temperatures, salinity changes, species distribution shifts, information that is increasingly important for understanding how ecosystems responded to past climate change and how they might respond to future warming. Of the archaeological sites evaluated on Santa Cruz Island, 50 were classified as highest risk, 115 as high risk, sites that will likely be destroyed by sea level rise, shoreline retreat, or storm erosion within the next few decades if current trends continue. The decision facing archaeologists is not whether to excavate these sites. It is which sites to prioritize, which to document before they erode into the sea, which to sample while there is still time. Because full excavation of all threatened sites is not feasible. There are too many, too much data, too little time before the ocean reclaims what has been exposed on land for millennia. The coastal archaeological record contains information about how past societies adapted to climate change, how they shifted resource use, how they migrated, how they survived or failed to survive when coastlines shifted and ecosystems transformed. That information is vanishing, not because the sites are fragile, but because the environment they existed in is changing faster than preservation efforts can keep pace. By 2100, under a high-emission scenario, global sea levels could rise between 0.5 and 1.9 meters, a range that, at its upper bound, would exceed nearly all previous projections. The IPCC's Sixth Assessment Report, published in 2021, projected sea level rise in the range of 98 to 188 centimeters under the worst-case SSP 5-8.5 scenario, with low confidence, high-impact estimates reaching as high as 1.6 meters. By 2150, the range expands to 0.98 to 4.82 meters, depending on whether ice sheet acceleration continues beyond 2100. By 2300, if emissions remain high and ice sheet instability triggers accelerated collapse, sea level rise could reach 9.5 to 16.2 meters. That is not a distant, abstract number. That is the height of a 4 to 5-story building. That is enough to drown every coastal city on Earth, to redraw every coastline, to submerge entire nations, to displace billions of people, to erase the geography we have built our civilizations around. The projections come with uncertainties. The exact rate at which ice sheets will melt, the degree to which ice cliff instability will accelerate collapse, the feedback loops between warming oceans and atmospheric carbon dioxide. All of these introduce variability into the models. But the direction is not uncertain. The ice is melting, the seas are rising, and the coastlines, ancient and modern, archaeological and contemporary, are vanishing beneath water that does not care about heritage, does not care about history, does not care about the 13,000 years of human adaptation and survival that are encoded in sites that will soon be submerged, eroded, lost. The sea does not take sides. It only takes. Beneath the surface, the ocean moves in currents driven by temperature and salt, thermohaline circulation, the great conveyor belt that transports heat and nutrients across the globe, that regulates climate, that determines which regions warm and which cool, that connects the Arctic to the Antarctic in a slow, continuous loop that takes approximately 1,000 years to complete. Water sinks in the North Atlantic, where it becomes cold and salty enough to descend into the deep ocean, forming North Atlantic deep water. It flows southward through the Atlantic basin around Antarctica, then northward into the Indian and Pacific Oceans. Then it eventually upwells, the oldest water that left the surface 1,000 years ago, finally returning to the light, carrying with it the chemical signature of a climate that no longer exists. The system is driven by density gradients, differences in temperature and salinity that determine whether water floats or sinks. When sea ice forms in polar regions, the salt is left behind, increasing the salinity of the surrounding water, making it denser, causing it to sink and pull surface water in to replace it. This process initiates the deep ocean currents that drive the global conveyor belt, that regulate Earth's climate, that determine how heat is distributed from the equator to the poles. If the system weakens, if fresh water from melting ice sheets dilutes the North Atlantic, reducing salinity, preventing water from sinking, the circulation slows. Heat transport weakens. Regional climates shift. The impacts cascade through the ocean, through the atmosphere, through ecosystems that depend on nutrient upwelling, through fisheries that depend on those ecosystems, through the human communities that depend on those fisheries. The conveyor belt has slowed before. During the Younger Dryas, fresh water from melting ice sheets disrupted the circulation, triggering a rapid return to near-glacial conditions that lasted over 1,000 years. Whether the current melting of Greenland and Antarctica will trigger a similar disruption remains an open question. But the possibility exists. And the ocean remembers how it responded the last time the ice melted too fast, the last time the salinity balance was disrupted, the last time the conveyor belt slowed, and the climate changed in ways humanity was not prepared for. The ocean does not forget. It cycles. It circulates. And what it learned the first time, how to redistribute heat, how to respond to freshwater pulses, how to shift currents and rewrite climates, it still knows. It is only waiting to see whether we will force it to remember. Maps are more than navigation. They are memory encoded in lines and coordinates, in coastlines traced by hands that no longer exist, in knowledge preserved through centuries when the world itself was changing too fast for any single lifetime to comprehend. The oldest known maps, Babylonian clay tablets from 2300 BCE, Egyptian cartographic representations from the Turin Papyrus, Chinese silk maps dating to the 2nd century BCE, were not drawn for exploration. They were drawn to preserve knowledge, to document boundaries, trade routes, sacred sites, the location of resources essential for survival. They were cultural artifacts as much as practical tools, embedding within their lines the worldview of the people who created them, what they considered important, what they measured, how they understood space and distance and the relationship between land and sky. These maps ignored the curvature of the Earth. They were not scientifically accurate in the modern sense, but they were culturally accurate. They represented the world as the cartographers experienced it, as their societies understood it, as the knowledge available to them allowed. And they survived, not because they were perfect, not because they were carved in stone meant to outlast empires, but because they were copied. Generation after generation, culture after culture, each inheriting the maps of those who came before, tracing the lines, preserving the knowledge even when the original sources were lost, even when the geography they depicted had changed, even when the world had moved on and the coastlines were no longer where the maps said they should be. The Piri Reis map, the Orontius Phineas chart, the medieval Portolan charts that showed Mediterranean coastlines with such precision they rival modern surveys. All of them are copies, descendants of older maps, inheritors of knowledge that predates the cartographers who drew them, holding within their lines a memory of voyages that were never recorded in surviving histories, of coastlines that existed before the ice came or the seas rose or the world was redrawn by forces too slow for any single generation to perceive. The maps still speak, quietly, patiently, holding their impossible knowledge like seeds buried in cold ground, waiting for a climate warm enough, intellectually, technologically, culturally, to recognize what they are and where they came from. Knowledge does not transfer automatically. It requires intention, effort, the deliberate teaching of one generation to the next, the preservation of practices and insights that would otherwise vanish when the elders die and the stories stop being told. Intergenerational knowledge transfer is how cultures survive, how traditions persist, how skills that took centuries to develop, navigation by stars, shipbuilding techniques, agricultural practices adapted to local climates, are passed forward so that each generation does not have to start from zero, does not have to rediscover what their ancestors already knew. The process is fragile. It breaks down when communities are displaced, when languages are lost, when younger generations move away and the connection between elder and apprentice is severed. And when it breaks, the knowledge vanishes, not gradually, not with warning, but suddenly, in the span of a single lifetime. But the last person who remembers dies and takes with them everything they learned that was never written down, never recorded, never transferred to someone who could carry it forward. Aboriginal Australians preserved oral traditions for 13,000 years through deliberate, structured teaching, stories told in ceremonies, repeated until memorized, embedded in song cycles that traversed entire landscapes, encoding geographical knowledge in narrative forms so precise that modern geologists use them to reconstruct ancient coastlines. The preservation was not accidental. It was engineered. Cultural pedagogy designed for durability, for transmission across hundreds of generations, for survival through climatic shifts and migrations, and all the disruptions that could have erased the knowledge but did not because the community valued it, protected it, taught it with the kind of care that ensures continuity. The maps are similar. They survived not because parchment is eternal, it is not, but because they were valued, copied, preserved in libraries, in archives, in the collections of scholars and navigators who recognized, even if they did not fully understand, that the maps held something important, something worth protecting, something that should not be lost even if the world it depicted no longer existed. Knowledge transfer is how memory survives past the limits of individual lifetimes. It is how we know anything about the past that was not written in stone or preserved in fossils. It is the thread that connects us to ancestors we never met, to cultures that collapsed centuries before we were born, to knowledge that should have vanished but did not because someone, somewhere, decided it was worth saving. To understand the maps, to understand how they could show Antarctica without ice, how they could depict coastlines that existed before the glaciers came, requires a shift in perspective, not from years to decades, but from human lifetimes to geological time, to deep time. Deep time is the concept that geological processes operate on scales so vast that human experience cannot hold them whole. It is measured not in generations, but in epochs, millions of years compressed into strata of rock, into layers of ice, into the slow drift of continents across the surface of a planet that is itself only a moment in the lifespan of the universe. Human civilization, in its entirety, occupies a minuscule sliver of this vast timeline. The age of cities, of agriculture, of writing and empires, all of it spans approximately 10,000 years. A blink, a footnote. The Holocene epoch, the current interglacial period that began 11,700 years ago when the ice sheets retreated and the climate warmed, contains the entire history of human civilization as we understand it. Everything that came before, the Pleistocene glaciations, the slow cycles of ice advancing and retreating across continents, belongs to deep time, to a scale where human memory is irrelevant and only the rocks, only the ice, only the slow accumulation of sediment on the seafloor can remember. Glacial interglacial cycles last approximately 100,000 years. For the past 2.6 million years, the Earth has oscillated between ice ages, when continental ice sheets covered vast portions of the northern hemisphere, and interglacials, when the ice retreated and the climate warmed. The rhythm is driven by Milankovitch cycles, subtle variations in Earth's orbit, in the tilt of its axis, in the shape of its elliptical path around the sun, changes that alter how much solar radiation reaches different parts of the planet in different seasons. When northern hemisphere summers receive more intense solar radiation, ice sheets melt. When summers are cooler, ice accumulates. Over tens of thousands of years, these small shifts in radiation compound, driving the planet into and out of ice ages with a regularity that becomes visible only when viewed across deep time. We are currently in an interglacial. The ice has retreated. The climate is warm. But the cycle is not over. In another 50,000 years, if natural orbital cycles continue uninterrupted by human activity, the ice will begin to advance again. The glaciers will grow. The sea levels will drop, and the world will enter another ice age, not because of catastrophe, not because of anything Earth did wrong, but simply because that is the rhythm, the cycle, the way the planet breathes across timescales we were never meant to witness but can now measure, can now predict, can now hold in our minds, even if we cannot feel them in our bodies. But we have interrupted the cycle. Carbon emissions, atmospheric warming, the release of greenhouse gases at rates unprecedented in the geological record, all of this is pushing the planet out of its natural rhythm. We are not accelerating the interglacial. We are potentially ending it, preventing the next ice age from arriving on schedule, locking the planet into a warmer state that could persist for millennia. By 2300, under high-emission scenarios, the West Antarctic ice sheet may collapse completely. Not thin, not retreat modestly. Collapse. The glaciers that currently hold back trillions of tons of ice will fail, and the ice will flow into the ocean, raising sea levels by as much as 5.5 feet by 2200, and potentially more if the collapse accelerates beyond current projections. The projections agree through 2100. Ice loss will increase gradually, predictably, even under current emissions. But after 2100, the models diverge. The future becomes uncertain. Some simulations show slow, manageable retreat. Others show rapid, cascading collapse, the kind that occurred 9,000 years ago during the early Holocene. When warm ocean water surged beneath East Antarctica's ice shelves, causing them to collapse and triggering a domino effect of ice loss across the continent. That ancient meltdown was not isolated. It was a cascading positive feedback, where melting in one area accelerated melting elsewhere through interconnected ocean currents, through changes in sea level that destabilized neighboring ice shelves, through the loss of buttressing that allowed inland glaciers to speed up and thin and contribute to further sea level rise. The system amplified itself, and once it began, it did not stop until the ice had retreated hundreds of kilometers inland, until coastlines had shifted, until the geography of Antarctica had been rewritten. The ice remembers. It holds the record of that collapse in sediment cores, in isotopic signatures, in the shape of valleys carved by meltwater that flowed when the glaciers thinned. And the climate models, informed by that ancient memory, suggest it could happen again, not in the distant future, not in deep time, but within the next few centuries, within timescales that matter to the descendants of people alive today. If it happens, the maps will no longer be impossible. They will be accurate. Antarctica's coastlines will emerge from beneath the ice. And the rivers, the valleys, the mountains that ancient cartographers somehow recorded will be visible again, not as myth, not as speculation, and as geography, and the shape of a continent that was known once, forgotten, and finally, slowly, remembered. Modern science has a habit of solving ancient mysteries. Not all of them. Not quickly, but gradually, with patience, with tools that did not exist when the mysteries were first recorded, with technologies that allow us to see what previous generations could not. The Antikythera mechanism, a bronze device recovered from a Roman-era shipwreck in 1901, baffled researchers for decades. It looked mechanical, intricate, with gears and dials that suggested purpose but revealed no immediate function. For years it sat in museums, catalogued as an oddity, a curiosity from an age not supposed to possess such sophistication. Then, in the 1970s, X-ray imaging and later CT scans revealed what the corroded exterior had hidden: an analog computer designed to track astronomical positions, to predict eclipses, to calculate the phases of the moon with a precision that rivals modern devices. The mystery was not solved by guessing. It was solved by technology, by instruments that could see through bronze, that could reconstruct corroded gears, that could translate ancient engineering into models we finally understood. LiDAR, light detection and ranging, has revolutionized archaeology in the past decade. Scanning landscapes from aircraft, the technology penetrates forest canopy, reveals subtle elevation changes invisible to the eye, and maps entire cities hidden beneath jungle growth for centuries. In 2023, a Roman military camp over 2,000 meters high in the Alps was discovered not through excavation, but through digital terrain modeling. Structures no one knew existed until the data revealed them. In 2024, LiDAR scans in Central America uncovered Mayan cities, road networks, agricultural systems spanning hundreds of square kilometers, rewriting our understanding of pre-Columbian civilizations and the scale at which they operated. The tools keep improving. DNA analysis that does not damage bones. Sodium phosphate dating. Artificial intelligence trained to read ancient texts, to restore inscriptions worn smooth by time, to decode languages that have not been spoken in millennia. Each advance reveals something previously hidden, something the past held but would not release until the right instrument, the right question, the right moment of technological readiness arrived. And with each revelation, history shifts. Not dramatically, not all at once, but subtly, in the way margins accumulate into new narratives, in the way anomalies become patterns, in the way mysteries stop being mysteries and become simply knowledge, waiting, as it always was, for the tools capable of uncovering it. The maps may never be fully explained. They may remain contested, debated, filed under unresolved in the archives of cartographic history. But they exist, and their existence, their impossible precision, their depiction of coastlines that should not be mappable, continues to pose a question that refuses to be dismissed. What if the world was known once, in ways we have forgotten? Not through divine revelation, not through extraterrestrial contact, but through human effort, through voyages taken during climatic windows when the world looked different, when Antarctica's edges were accessible, when coastlines extended farther and trade routes connected lands that are now separated by risen seas. The knowledge would have been fragile. Oral traditions, sailing directions, charts drawn on materials that decay. But if it survived, copied, recopied, passed forward through channels we can no longer fully trace, it would eventually surface in the hands of Renaissance cartographers who no longer understood what they were copying, but preserved it because it was old, because it was precise, because it came from sources they respected. And if climate change continues, because the ice melts as the models project, because Antarctica's coastlines emerge from beneath the glaciers within the next few centuries, because the maps will finally be verifiable, not through speculation, not through reinterpretation, but through direct comparison. Coastlines mapped by radar, by satellite, by the instruments we finally possess, matched against the lines drawn on parchment centuries ago by cartographers who should not have known but somehow did. The future may prove the maps correct, or it may prove them wrong. But either way, the question will be answered. In history, our understanding of who knew what, and when, and how, will shift accordingly. The maps still speak, not in voices, not in arguments, but in lines, traced carefully, preserved patiently, waiting for a world willing to listen, a technology capable of verifying, a climate warm enough to reveal what the ice has hidden for so long. They do not demand belief. They do not require faith. They simply wait, as the ice has waited, as the sediment cores have waited, as the fossils buried in Antarctic rock have waited, holding the memory of forests that grew when the continent was green, holding the shape of a world that existed before the ice came and buried everything. The planet remembers, in layers, in isotopes, in the slow accumulation of knowledge that does not vanish but transforms, from experience to oral tradition, from oral tradition to written record, from written record to map, from map to archive, from archive to rediscovery. And when the ice melts, if the ice melts, the memory will resurface, not as myth, not as speculation, but as coastline, as geography, as the undeniable shape of a continent that was known once, forgotten, and finally, in 12,000 years of silence, remembered.